কিছু বলছিলে ঠিক আছে তাহলে শুরু করা যাক নাকি Okay, so good morning, and as we all know, we are coming close to the end of this fascinating 5-day session, and today it was kind of a little bit of change at the last moment that we had to do because of some issues. So I will be giving the first lecture today, and today's talk will be very less of physics, a bit of technicalities. I mean, like we would like to ask this question that how can we make effective use of these effective operators that we have dealt with so far, and I will give you a glimpse of that. Of course, I mean it's not a complete description, but there are more that one can do, and I will explain as I go along. Okay, so so this is the question, what do I do with these CFT operators that I am studying? Well, depending on your physics interest, you can study Higgs physics, say for example, or you can study dark matter physics with them. You can apply them to the neutrino physics. You can in general study collider observables and the contributions to the signals, etc. And in all these cases, a numerical implementation of these operators is often very helpful. There is a slight warning that it is not always necessary that, for example, if you just want to study the cosmological evolution via Boltzmann equations, you just need to compute the annihilation cross sections of the dark matters. It is not strictly necessary, but you never know that whenever you are calculating something, there might be some errors or mistakes that you might be doing in the process of doing those numerical calculations. On the contrary, if you successfully embed an EFT operator in some of these numerical tools that we will be talking on, you can actually be sure of some of the basic ingredients with which these EFT operators are constructed and its further calculation, like for example gauge invariance, which we have been all talking about, that can be checked thoroughly and etc., which while doing by hand or using by Mathematica and putting that expression over there to calculate the numerical outcome might give you something wrong. So it's better that you actually put these operators in this numerical tool, check their consistency, calculate their cross sections, and then you match to your analytical calculations what you are doing. Okay, all right. So this is just a glimpse of the landscape of numerical simulations that one can do. So this is the part which we will be mostly talking about, that getting the operators embedded in fine rules, which will help you generate the Feynman rules and the vertices associated with them. And then there are other packages also which you can use. For example, LANHEP is easier and it is more useful for dark matter related calculations. SARA is often helpful to kind of do this renormalization group running and so on and so forth. I will mostly talk about how does the fine rules actually look like. Then there are certain files that you can generate with these fine rules, which has all this set of particles, the vertices, their properties, parameters, etc., which you can then feed into some matrix element event generation like MATGRAPH, CalCAP or Sherpa. CalCAP was the one that we actually all started with. It was, I think, one of the oldest software which calculates all these cross sections numerically. MATGRAPH is the most modern one that you can actually use, and then there are showering hadronization that you can do using Pythia, and that is almost embedded in this MATGRAPH tool. And so what thing MATGRAPH does that CalCAP cannot? There is a simple answer to that, that whenever you have 4 body final states, say for example, you are producing, say for example, ZH, and you want to also have this Z going to L plus L minus, H going to BB bar, and so on and so forth. So whenever you want to calculate, say for example 4 body final state, I mean using ZH, that is a trivial example, but you can have a new physics example, say a heavy quark which is decaying to a light quark and a Z boson and so on and so forth. Calcap can still do that, but the problem is it takes enormous amount of time. So that's one. Whenever you have a large final state, then Calcap 2 going to 2, it's very easy, but to NLO calculations, I'm not sure if Calcap can do.
It can provide effective
vertices.
It can just calculate, but it cannot do NLO.
Yeah. So NLO calculations also, for example, you cannot do.
One point to add is that Sherpa does its own part-on showering.
Oh, Sherpa has this own part-on showering program. Also in MATGRAPH, as far as I know, that you can calculate the cross section in different ways. One is the usual trace technology, and the other is actually using helicity amplitude technique. I think MATGRAPH does using helicity amplitude, so this is very, very faster. Whereas Calcap does it using the trace technology, so that matrix element squared, etc., etc. So therefore, it is the helicity amplitude you can produce. Yeah, exactly. So so then the part-on showering and hadronization you can do using here, and then if you are interested in more sophisticated event generation, you can do this detector level simulations using Delphis, and okay, I think this arrow is a kind of a mistake. So for example, you are interested in dark matter physics, like calculating the Relic densities, the direct search prospects of these effective operators, then I think it is directly from fine rules that you can go feed files which are compatible with micro omegas. Actually, this is same software of Calcap, which is which has this additional calculation possibilities, and now micro omegas is actually equipped with all these different kinds of possibilities, like you can have a 2-component dark matter, you can have extended dark sector with co-annihilation effects and all that, which was not there earlier, but nowadays it's more sophisticated, and here you can do those kind of calculations, and of course then you can merge them together to do whatever analysis, this parameter space scans. The numerical routine that you have to run over different set of parameters, that you have to write that kind of code, whatever Python or etc. But you can call them in loop or something, and then you can generate your parameter space scans, which is compatible with your dark matter searches, collider search prospects, and so on. So this is a rough sketch of what usually people do, and as I said that I will give you a quick introduction to fine rules, and it's basically a Mathematica based packages, and it generates output as we just discussed for MATGRAPH, fine arts, Calcap, etc., etc. And what one needs to do that this fine rules automatically embed standard model, and it has many effective operators also. So I will give you some examples as I go along, and how do they look like, and etc. So so these are the files that you usually have in the fine rules, and there are some files which are like Cabibo, diagonal CKM, massless. These are .rst are the restriction files, which basically says that these are better not to touch. The files that we usually have to modify, or rather if you want your new interactions to be embedded, is this .fr file. Okay, so this is the model file that we will mostly talk about, and then there is this implementation notebook, which is the standard mathematical notebook. It's called sm.nb, and smqcd-nlo is the additional file used for generating UV and IR, I think, counter terms. R2, okay, okay. So, what is there in the standard model file, say for example sm.fr. Now, you can imagine that these are the basic informations that you have to have. Well, I mean the model information, the index definitions, which is basically the preamble, if you can say. Then you have to have the declaration of the fields, name of the particles, spins, PDG codes. This is something interesting, that these PDG codes of the particles are already decided for the standard model particles and also for supersymmetric particles. But if you have, so for example, you want to embed a vector like fermion and you want to study its prospect, then you have to devise a PDG code that does not match with those ones, and then and of course, you have to define their indices, quantum numbers, the masses, widths, classes, and etc. And then you also have to declare the gauge group, like it's abelian or not, representation matrices, the structure constants, the coupling constants, gauge boson or vector superfields, etc. And then of course, the parameters that go into the Lagrangian. You can devise it in two ways, like you have the external ones that are the independent inputs that you want to give, and the internal ones will be the ones that will depend on those external ones. So, this is basically the content of this .fr file that you need to be you need to work upon, and finally, all this constitutes the Lagrangian as a whole. Okay, so yeah, this is the first part, which is the preamble, that you do this model name. Say for example, this is standard model, and then you have the information like here, for example, these guys are the ones who wrote it, and then version, date, etc., etc. This is something which is optional, as you can understand. And this is the part which actually talks about the standard model gauge group. Now, we all know the field strength tensors in standard model, like B mu nu is del mu B nu minus del nu B mu, W mu nu is the SU2 field strength tensor, which has another additional index I, and this is actually having this additional term because of the non-abelian gauge group, and this is for the SU3, this is for the gluon field, and once again these are the structure constants associated with SU2 and SU3. Yeah. So, here for example, you first define the gauge boson associated with this U1y. So, this is abelian, that it's true. Coupling constant is defined as G1, the gauge boson is named as B, the charge is Y, which is the hypercharge that you remember we talked about. Now, you do it for SU2L, and this is not abelian, so that is false. The coupling constant is defined like this, gauge bosons are defined like Wi, the structure constant is epsilon, so this is defined, and these representations are Ta, SUD, the Ta, A, B, C, these are essentially the generators of the SU2, which are Pauli sigma. This is I think already defined in it, and then you have this f of SU2L ijk, which is I epsilon. So, this is I think the commutation relation, right. So, which is I epsilon ijk, which defines the structure constant associated with this thing. So, for SU3, once again, I mean it is a similar thing, and usually what happens that we do not unfold the SU3C part, because particularly if we are interested in embedding SU2 interactions or electroic extension of the standard model, which we mostly are doing. So, that I will come to the next slide actually, but this is the part which therefore is most important for us. And yeah, okay. Yeah, now this part is interesting, because you have basically unfolding this. There are two nomenclatures you see, this is SU2W and this is SU2D, and you see that SU2W has a range 3, whereas SU2D has range 2, and this you can understand that there are two representations of SU2, one which is the adjoint representation in which the gauge bosons transform, and the other is actually the fundamental representation in which the particles, I mean the doublets actually transform. So this SU2D will refer to actually the transformations of the quarks and the lepton doublets, whereas for SU2W it will be the corresponding gauge bosons. Okay? So this is what you do, and as I said that we usually do not unfold the gluon and color indices. So this is usually the no unfold once again, but you have those possibilities, like you have both the representations, the adjoint and fundamental representations associated with SU3 for triplet and 8 gluons which are followed from the adjoint representation of the SU3. And here are the indices which are defined corresponding to each of these, because when you expand them, you know, for example, for SU2W there will be 3 sort of vector bosons which will be defined like Wj, where j will run from 1 to 3, and then for SU2D the index will be k, and that will run between 1 to 2. For gluons, A will run from 1 to 8, for color M will run from 1 to 3, and then there are generation indices or flavor indices, whatever they are. However, while we are writing the interaction terms in the Lagrangian, we better be consistent with these indices that we define here. Now there is another important point which is actually about the interaction hierarchy. So basically this shows the priority, like QCD whenever that is there, it will actually be the dominant one, and QED will be the subdominant one or will be neglected, and this is usually the M dollar interaction hierarchy, interaction order hierarchy that we have. And whenever you have new physics in it, because you want to prioritize it, the way that we do is usually we put the new physics comma 1. I think this, if you put new physics comma 2, I think it can get neglected, right?
It depends how you write in that graph. So if you explicitly mention that you want this, then it will be taken, but if you don't mention,
then this dominant contribution will only be taken. Yeah, vertices will be generated for all the cases, but it's the priority that you decide. Yeah, yeah. So yeah, this is the part which is important for us, which will embed the cases for BSM, EFT, etc. Okay, now these are the particles which are already defined within the fine rules, and these are something that we have came across, that the fermion fields, you know, you can have two different representation, one representation which by which we write the standard model, which we have all talked about, like left-handed lepton doublet, right-handed singlet, right-handed lepton singlet, left-handed quark doublet, right-handed quark singlets. On the other hand, you can have this physical fields defined by UQ, where UQ defines UCT with their electromagnetic charges, DQ defines the down type quarks with their electromagnetic charges, but this notation like UQ includes U, C and T, DQ includes D, S, B, L includes electron, muon and tau, and nu L actually defines all these 3 flavors of neutrinos, nu E, nu mu and nu tau. Then there are vector bosons, and once again you can have them in the unphysical way, which the way that you actually insert them in the standard model Lagrangian, like Wi and Bi, and then the physical basis of the gauge bosons like the photon, Z, W and gluon. And similarly you can have the scalar bosons the way that we have, that this is the unphysical isodoublet, and these are the physical fields like the Higgs, Goldstones, I mean G0 and GP, referring to these 2 Goldstone degrees of freedom. And then there are ghost fields here, which you know show up, but the point is defining, depending on which gauge that you actually want to work upon, these ghosts and goldstone fields can become important or not. We know, for example, if you are working in unitary gauge, the interactions with the ghosts and goldstones becomes unimportant, but if you are working in what is called Feynman gauge, then this actually will play a part. So, yeah. Yeah, there is a kind of ignorance about these fields because most often while we do theoretical calculations, we work in unitary gauge, but please remember that if you are not using unitary gauge, this is very important and we should take care of this part. Now, let us talk about the fermion fields. So, this is the class name. So, this is the one which defines the physical fermions, like for example, L, which has this electron, muons and taus in it, and the indices will have the generation index, as you can understand that it will have 3 generations like electron, mu's and taus, and these are not self conjugate for sure. You have to define their masses like mass of electron, muon, tau, so on. You assume the decay width to be 0. I think you can, if you wish, you can include the decay widths of muon and tau if you want. Then the quantum numbers, because these are the physical fields, so here there are 2 quantum numbers that we actually associate. One is the electromagnetic charge and one is the lepton number. Okay? So, quantum number is therefore electromagnetic charge -1 and the lepton number is 1, and there are propagator levels that you can set, propagator type, you know, the usual way that we draw the Feynman graphs associated with the fermions, like straight with an arrow forward, and these are the standard PDG code for electron, muon and tau, and then there are these particle names that you assign, and then there are these corresponding antiparticles and the full name. So, this completes the definition of L. Similarly, you can imagine, you can define this class for the physical quarks, right, for Q, and which will include you know, QU like up, charm and top, and similarly for the bottom one, etc. Now, this is the one which is the unphysical one, but importantly this goes into the definition of the standard model Lagrangian, because this is exactly where you define them like the left-handed doublet. So, once again the class name is LL, as I just mentioned, and these are unphysical, which is true. Indices, now here you see that this index is coming into play. You remember that SU2 has 2 different representations. SU2W was the adjoint one and SU2D is the fundamental representation. So, here the index will be SU2D, and there will be of course the generation indices, and the flavor index is associated with this SU2D. These are not self conjugate, and we remember that in order to be consistent with the standard model, Q is equal to -1 associated with the electrons, and for neutrinos equal to 0, we had this Q is equal to T3 plus Y. So, the hypercharge associated with the doublets was actually Y equal to -half. Now, say for example, you want to define a new vector like fermion doublet. Okay? So, what will be the change? You associate what kind of vector like doublet that you want to add to the story, you define a name, and you have to use this index SU2D, you have to define your corresponding hypercharge with which you want to define that additional vector like doublet. The one important point here is to note that here the components that constitutes this left-handed doublet are having left-handed projections. So, therefore, that is how you have this included in it, like PL multiplying each of this component, and that is what this project M. This project M is actually the PL operator, which is half into 1 minus gamma phi. Okay? And this will have to be embedded explicitly in this particular way, and this is basically the matrix multiplication, if you may say. Okay? And the same happens. So, this SP1 1 is the component up, SP1 2 is the component which is down, and that both has to be explicitly multiplied by this PL, which is defined by project, I mean whatever that you say, proj m or whatever. Now, so this was the case of left-handed doublets. What about the right-handed singlets? The right-handed singlets are like LR, and in this, of course, you have to have, because they do not have any isospin, so the quantum number of electromagnetic charge is essentially fed from this hypercharge only. So, y is equal to -1, and the definition is simply LR sp1 ff, and here you see that it is not a matrix unlike this LL case. It is a singlet, so therefore, the only entry is project P sp1 sp2, and this is the usual multiplication for each of these components. So, this is like ER is equal to PR into E. So, this is basically the definition by which you can do. So, this goes for all the cases, you know, for the quarks also. Okay? It is okay? Makes sense? Now, let us come to the case of vector boson, and so once again you do this mass, width, particle name, quantum numbers, PTG code, etc., 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 and these are the physical ones, and then there are these unphysical ones actually which enters into the standard model. Now, here you see that we are defining this B mu in terms of the physical ones. So, Z mu minus sin theta w Z mu plus cos theta w A mu, the relation that you have already come across. So, similarly, this is for the you know, hypercharge field, and this is for the Wi, and here you will have to have this index SU2W. Once again, I would like to remind you, there are two representations. This Wi are transforming under the adjoint representation of SU2. So, the index will be associated with SU2W, and then you have this Wi1, Wi2 and Wi3, and we are defining them in terms of the physical W's like W plus W you know, W1 plus IW2 by square root of 2 and so on. Okay? And W3 is the one which is cos theta WZ mu plus sin theta W mu. So, this completes the definition of the vector boson. So, now you can define the scalar boson exactly in the similar way, and the indices will actually involve the transformation of the Higgs doublet under the fundamental representation of SU2. So, therefore, that is what is here. You have to define its hypercharge. We all argued that the usual way that we write the standard model Higgs doublet has this hypercharge of half, and the definition is that you now explicitly write that this is the Goldstone in the charge associated with the phi 1 plus I phi 2. If you remember in the definition of the Higgs doublet, this is what is the GP, and then this is the physical part which is actually there, which we all write in terms of unitary gauge, but there is this additional piece like IG0 associated with phi 4 field, which is the another Goldstone degrees of freedom. So, this is explicitly a definition, and here define depending on whether the Feynman gauge is true or false, the Goldstones can be turned on or off. Now, you come to the parameters. This part is not very difficult. The thing is, you define this alpha s at mz, and which is actually Ga square by 4 pi. So, this has a QCD of QCD degree of order 2, if you may say, or QCD order of 2. And this is the one that you define, that alpha s mz with its value. So, therefore, the internal parameter correspondingly will be this Gs, which actually enters into the Lagrangian once more, and the interaction order will be QCD1. Okay? And you can define the parameter name, etc., etc., etc. So, it is defined as square root of 4 pi alpha s, where alpha s you have defined as an external parameter. Therefore, the Gs is an internal parameter. Now, with all these ingredients, you are there to write the Lagrangian. So, this is the generic form that you have a block, then you have all the indices with your piece of Lagrangian actually have. Then you expand indices and then you write the Lagrangian, flavor expand, the flavor this thing, and if there are some conditions, I will come to this point when we actually write at least some part of the Lagrangians. I will explain what kind of conditions that you may mention here. So, yeah, in this flavor part you have basically the SU2W and SU2D cases, I mean both the fundamental and adjoint cases, and these conditions include this possibility of using Feynman gauge or not. And these indices will have all kinds of indices, like you remember for fermions you have a spinor index, Lorentz index is there, I mean for all these vector boson fields, also with the gamma mu's which actually go in. Then there are cases of doublets which you have this indices II, JJ, KK, the color indices are AA, the flavor indices are FF, and remember these indices, the notations of these indices have also been defined at the very beginning of writing down what kind of indices that you want to assign for each of these different properties, and it is usually the customary that we do not sort of mix and match, because then the Lagrangian will be not complete. So, the total Lagrangian is of course in the standard model Lagrangian, the gauge Lagrangian, the fermions, the Higgses, the Yukawas and the ghost terms. So, for example, let us look into the gauge part of the standard model Lagrangian, which we all know that it has this QCD part, this is the SU2 part, SU2L part, and these are the U1Y hypercharge field strength tensor associated with this thing. So, let us say for example, look into this thing, and this as I said that this is this block. What are the indices? You have the Lorentz indices mu nu, II was the indices associated with this SU2W, so that is there, and AA is the index corresponding to this color index, also in the adjoint representation, and then you expand indices writing -1/4 Fs B mu nu, Fs B mu nu, and in general this Fs is essentially defining the field strength tensor. So, the generic notation is field Lorentz index 1, Lorentz index 2. So, this is the way that you can do, and this is exactly what it is. So, you have this thing, and then you have to flavor expand in terms of SU2W. You can do this expansion for the SU3C case also, but that will unnecessarily make things complicated and not required for the purpose that we are actually going to look into. Any questions here? Okay. So, now let us come to the fermion part of the Lagrangian. So, we know these are the kinetic terms which are there for the left handed doublets, for the right handed singlets, okay. And so, therefore, once again this involves the index.
Sir,
yeah.
I have a question.
Yeah.
That in the beginning you showed 3 restriction files, one of them was the mass restriction. So, if I work with a model where I need to have some massless particle which are already there in massless condition, they are considered in the file some particles are considered as massless. So, you told that we we should not touch the files.
No, I mean yeah, I mean yeah, you asked the question.
So, suppose I am working with a model and in a particular scattering I want to observe. So, there I need that a particular particle to be massive. So, can I change there in the
I think you can. I mean, it's not something very difficult. Usually, there are light quarks and light electrons, leptons there in the massless. I mean, but changing them to be massive is not something very difficult. Yeah.
Their QCD, QED and new physics. So, in the parameters we have to write that thing, that QCD in the order block, QCD comma 1 or something. So, if I write for the BSM particles or some new particles, that new physics comma that order or something, will that understand that it is, I mean,
yeah,
the meaning?
I think it works fine with this new physics comma 1. I mean, because it automatically then prioritizes that you have to take into account the new physics contributions. If you put as Shankho mentioned, because he is more expert in this part. So, if you put new physics comma 2, then depending on in MATGraph in particular, that if you want to, it may or may not take into account this higher dimensional operator contributions in that particular case. So, therefore, it is important that you keep the new physics preference as equivalent to the QCD. So, that is taken into account.
Also, we are defining the indices at the beginning.
Exactly.
And while writing the Lagrangian part wise, can we redefine or rename the indices in the local
You
scope?
can do, but then you have to unnecessarily change the whole standard model Lagrangian. So, my idea is to not to kind of fiddle with the standard model Lagrangian too much, but include those operators, higher dimensional effective operators, or the new physics that you want to address based on the kind of like SU2W index, SU2D index, SU3W, SU3D, etc. So, these are already defined like II, JJ, KK, etc. Flavor indices are FF. If you fiddle with that, then you have to be first of all consistent, because the whole standard model Lagrangian you have to change. Secondly, it does not serve the purpose. You can do it consistently. I mean, it is not a very difficult job, it is just a little tedious that you have to rewrite the standard model, and then you can sort of write whatever. Then you say, for example, you want to introduce a vector like doublet, right handed neutrino to be inserted in your model, right. So, then you have to right handed neutrino is okay, because it is a singlet under the standard model, it will only have the flavor index. But for example, if you want to include a vector like Lepton doublet for some reason, then it is easier that you stick to the indices notation which is defined in the standard model, and you just rename the particles which enter into the doublet. So, as I said that for instead of writing that LL, you can follow exactly the same block, you can write a block without having those projection operators embedded to define them. So, that will do your job. If you want to include a triplet, say for example, you can do exactly in the same way, because you also have this adjoint representation and you have that indices over there. So, you can do that. You want a Higgs quadruplet, you can follow the Higgs doublet pattern and then just use the flavor indices to expand how you want your matrix to be. The definition of matrices are also there, so you can use that purpose. So, changing the flavor indices is not a good idea, because unless you are having a new gauge group. So, for example, you want to extend your model with a new gauge group like an additional U1x, then of course, you have to devise a new index associated with that. But otherwise, it is easier. If you want particles to be transforming under the standard model gauge group, I will come to the case of Z2 symmetry later, which is often required for embedding dark matter particles into it, but otherwise changing indices do not help much. Yeah, but changing the mass is trivial, but changing the CKM and PMNS is a little more complicated. I think because there are restrictions, you know what are the experimental numbers and etc. Yeah.
Thank you.
Yeah, so so this is the part which does the case for. So you see this QL bar, gamma mu, DC of QL mu, etc. And then you have for LL, UR, DR, etc. And this flavor expansion has to be done both in SU2W and SU2D. And here there is a restriction that this VCKM IJ, VCKM JK dagger equal to delta IK. This is something that we have to assign to this fermionic Lagrangian. Then of course, there is another part, there are two parts essentially. One is the Higgs part. I mean, once again, here the one part which is important is actually this Feynman gauge rules, because if not Feynman gauge, then these goldstones actually go to 0. So, this is the part which is interesting in that particular context, and the rest is essentially very similar to what we have defined. You define plus mu h square, phi bar phi, etc., lambda phi dagger phi, phi, then you have the flavor expansion exactly the way that we wanted to do. And then the last part is the standard model Yukawa Lagrangian, and it is once again, it is not very difficult to kind of find The only thing is which we didn't write explicitly in our first lecture was the presence of this, I mean we wrote this U, matrices, but you all know that these have this additional CKM elements entering into it. So, which actually comes here. If you see that the corresponding YD FF2 FF3 then says CKM FF1 FF2 then QL bar FF1 and this DR FF3 and then you have the phi 2. So, this is a consistent matrix multiplication, nothing more than that, which takes into account this indices ij here, and however you also have to remember this is a doublet. So, that index goes in and the spinor indices are associated here with this QL bar and also with the DR. So, but this you have anyway defined before, so it will not be very difficult for you to kind of associate with each of these term, and the flavor expansion here will only be SU to D. And once again you have the same condition that this VCKM dagger VCKM will be equal to 1.
So, for why we don't expand the SU3 part here? So, you have told
the SU3 part, see the point is SU3 part of the Lagrangian, I mean we can expand, but I don't think it is going to give you, I mean it depends on your choice. So, for example, if you want to embed suppose supersymmetry in your model which has this SU3 particles, I mean particles transforming under QCD gauge group also, there you require. But the purpose that we are doing, which is an extension of the electroweak physics, we don't require it. So, that is my statement.
if BSM particle don't transform under SU3,
You don't fiddle with that. Yeah, exactly. If you want to do that, vector like quarks, Sanjay, right? So, in that particular case, if you want to do that, then you have to kind of expand that part also. So, yeah. So, but if you just have the electroweak extension of the Lagrangian, we are good enough to go with this part. So, now is the most interesting thing. So, let us try to address this SMEFT operators there are 3 examples which are shown here, and instead of going painstakingly through each of these cases, let me kind of take one example and I can we can see how exactly they can be added to the standard model Lagrangian, and that will do the job. So, for example, let us say this Higgs current operator, which looks like phi dagger I d mu phi, where there is this 2 arrows on the d mu, which basically means that phi dagger I d mu double arrow phi is essentially phi dagger I d mu phi minus I d mu phi whole dagger phi. So, this is what it is, and also the sigma mu nu, all of you know that this is I by 2 gamma nu commutator. Okay. So, this has to be explicitly mentioned because they do not know the definition of d mu this thing, and they do not also know sigma mu nu, but gamma mu all these are there within the within it. Okay. So, yeah, now this is I mean in order to do this you have to basically define first the parameters. So, what are the parameters? You are assuming here for simplicity that there is only one new physics scale lambda, and then there are 3 different Wilson coefficients. I mean when you are including all the 3 operators, say for example together. So, these are the CW, CHQ1, CLEQ3, and so these are easy to understand. These have interaction order NP comma 1, which she wanted to clarify. So, for all of these cases you have this interaction order NP comma 1. For lambda, this new physics scale, this is for some reason. So, for example, you here you assign the value 0, but that is just I mean you can assign any value that you want. And here the warning that Jose actually gave to you may come into play. like if you are inserting operators which are involving gauge field strength tensors, if you assume weakly coupled and decoupling new physics, then they might come at the loop level only. And so here in the value, instead of quoting 0.1 or something, you have to include that 1 by 16 pi square explicitly if you want. Okay? So this is, you can also put that in the Lagrangian separately. You can put it here also. If you are varying the parameter, wherever it is easier for you, you can do that. The one thing that I wanted to draw your attention to, that this lambda, which is, say for example here 1 TeV, this has unit of mass, and so therefore the interaction order is written like QED minus 1. So this is one part. So for the dimensionless new physics couplings, that is actually new physics comma 1, but for mass parameter like lambda here, that has a unit of mass, and so that is written like QED minus 1. Why this is actually done, I don't know. I also don't know. Shankho? I mean, this is funny, but this is how it is. Yeah, QED minus 1 sounds a little funny, but it says that if you want to include the dimension full parameters, whether it's 1 by lambda square, lambda cube, that will automatically be taken care of when you write the Lagrangian. But while defining the lambda,
basically it's vertex. So
it's
how they define the vertex factor? Suppose E, electromagnetic constant. So that depends on that.
Yeah. So I think Deepankar is absolutely right. Yeah.
Also they have
order for
They have order for wave also. Yeah, but I mean, so this is because I think his answer is in a sense that it is because C by lambda is coming in the vertex factor. So that's how this is QED minus 1. Yeah. Okay, all right. So this is the operator which I was telling you, that we have this C1 HQ lambda square phi dagger I d mu phi QL bar gamma mu QL. So what you can do, that you can define these two parts separately, like phi dagger I d mu phi is this part where you have to include the Higgs doublet. So therefore the same point arises, Feynman gauge rules, if not Feynman gauge, blah blah blah, expand indices in terms of, so there are only these indices associated with SU2D, and then you have you define this phi dagger I d mu phi as we just wrote in the last slide, and this is this DC, you remember, is the covariant derivative associated with each field, which is defined. So DC of phi is already defined. So therefore you can simply take that and just put the indices, the SU2 index and the mu index, which is the Lorentz index, and you define explicitly. And so this is this part. Okay, and then you have QL bar gamma mu QL, that is easy. So you have this QL bar, this QL, this is the gamma mu, and you must have to make sure that this matrix multiplication is correct, and that's it. And in both cases you flavor expand in terms of SU2D and SU2 this thing. So then you say that, okay, so all right, actually this has explicitly this part, I must say that this is explicitly this part multiplied with this HDH mu, which we defined as for this one. Now this is a nomenclature which is up to you. You can call it anything. HDH is something that is that we wanted to define it, but you can define it in any different way. So this is explicitly this part multiplied with this part, which is defined here with this prefactors somewhere sitting. Yeah, this is here. So this is SL, this is this thing, that this guy with this guy by lambda SMEFT whole square. So this does the job for you. Now I do not want to go over for the cases here, so the slides will be there with you, so you can actually look into. Now let us come to this part, that suppose you want to add any dark matter operator. I beg your pardon for this typo. These are not the dual fields that we are inserting. I mean, this is W mu nu only. So, with say for example, zeta square. So, this guy, this zeta is now the dark matter. So, we are defining an effective interaction between a scalar dark matter with the field strength tensors of the standard model, say for example. Now, if I had to do this, what additional thing that you need to do that you didn't do in the previous exercise? The first thing is that this new dark matter field is not defined in your Lagrangian. When you are defining the standard model Lagrangian or writing the effective operators with the standard model fields, all the fields are defined. So, you just have to define the operator using them. But when you are doing the dark matter case, then first thing that you have to do is to define the dark matter. So, for example, here you want to have this to be a scalar dark matter. Now, you give a name, you define the mass, it does not decay, so it is 0, there is a propagator level, etc. PDG code, you put something arbitrarily large, and so that there is a less chance to get conflicted with the existing one. There is an interesting point which I must draw your attention to, is that in the particle name you must define the dark matter with a tilde, whatever, tilde A, tilde B. Why this tilde? This makes sure that you will only generate vertices which are protected by the Z2 symmetry of the Lagrangian. Okay? So, this tilde ensures that, because otherwise you have to define the Z2 symmetry explicitly or something. So, this is the easiest way that you can make sure that this does not have a special symmetry or a special charge which other standard model particles do not have. So, similarly, for the scalar, the way that you have done, for the fermion you can also do a dark sector doublet, right. So, this is a dark sector scalar singlet, this is also a dark sector fermion singlet, but you are not happy. You wanted to have an extended dark sector. You wanted to insert, like Sanjay wants, to insert a doublet of the vector like quarks, which is protected, say for example, by Z2 symmetry. You can do that. But you have to then define exactly similar to the LL case, but with the tilde as their inputs for each of these fields that go inside this thing. So, this symbol allows the packages like micro omegas to identify the dark matter candidates. So, if you do not do that, then they will get confused. And this part is trivial, which I just talked about, and this part is also not very difficult, because we have defined this Fs B mu nu, once again ignored the tildes here, and then this xi square, the flavor expand is SU2W and SU2D, and so on and so forth. So, this is how exactly it goes. There is a special interest for which we wanted to write these operators of this particular kind, that physics is very interesting, but perhaps it is not time to talk about that kind of a physics, because this generates actually a kind of dark matter interaction where the monophoton missing energy distribution is completely different from that of the standard model background, which is produced by the neutrinos. So, therefore, it is kind of interesting for that reason, but then finally, whatever operators that you have already inserted, you have to add them all together, and then you basically have to do the implementation via this Mathematica notebook, and you do operations as follows. You can load the model. You can, this is a very important check, that you can check the hermiticity of the Lagrangian that you have inserted, and if everything is fine, it will actually generate all the Feynman rules for you. Now, these are complicated to look into, but we all have Cheng and Lee or any quantum field theory book that you write. So, there you can explicitly check whether the Feynman rules that you are generating using this package is okay or not. So, these are all the standard model ones, and then you have these additional pieces for the SMEFT. For example, this vertex HHZ UU, which is coming from one of these operators that we inserted, that is actually here. Okay. So, if you are doing an analytical calculation, you can also check the consistency of this using the analytical calculation. And similarly for the DMEFT case, you can check this is chi AZ interaction that you are generating, and there is a fine the corresponding rule is here. Yeah. So then the part which we couldn't talk about, that then there are options in the fine rules that you can generate the files which are compatible with incorporating in MATgraph, which are called this. So these are the commands, for example, write CHO output. This will help you to feed the model into micromegas and do your relic density and direct search calculations. This will allow you to feed the right UFO files. So these are the files which are usually fed into MATgraph, and they will do all kinds of collider simulations for you. You can also feed this into fine arts, and this is the command by which you can actually do that. So with this, I think I will end. So this is basically, so this file will be there with you. We are going to provide you an explicitly zip file with this actual SMEFT and DMEFT operators imported there. What you have to do, that you have to install Mathematica, you have to install the fine rule package and run those files to see exactly whether we are consistent, and you can do a phenomenology. So that we will do via email. So no, not here. Yeah. Okay. If they can do it here, I have no issues. But yeah. Okay. So with that, I will stop. So there are a lot of other things which one could have talked about, like the implementation and how would, one can do the MATgraph calculations. But yeah. Okay. All right. With this, I stop. Thank you. Oh, okay. Whatever that you want. So, but unless you do that, it will not be yours. Yeah. Any questions? Yeah.
So while mentioning the model information at the beginning, we have to mention the interaction order, and in that we have to write QED1, QCD1. So I have often found like error with those orders. So when we include any new physics particle, so what does that imply? And if we want to include in new physics, so sometimes I have written like NP1 and then it works, sometimes it doesn't work. So how?
Yeah, usually NP1 does work. I mean, when you write NP comma 1, then it takes into account the new physics interactions that, or the vertices that you generate. The problem is that suppose you want to do a calculation like E plus E minus to ZH, or PP going to ZH, as Shankhu was talking about. Now you have this operator that we have included this within, and you defined NP comma 2. Then there is a possibility that it will not take. So then you know that we saw that there is a contact term like QQZH, which should actually contribute or interfere with the standard model graph, right? So the point is, if you define NP comma 2, there is a possibility that it may neglect it while doing the collider computations. So that's the worry. So because we do want our new physics to come in, or the effective operator contributions to play part with the standard model contribution, so it is always good to keep the new physics to be NP comma 1. So then there is no chance in missing. But Shankho, is there any further comment that you want to add?
That's all.
Yeah.
So you can generate, let's say, AB when you set NP1 to 2.
Yeah.
You can do like AB going to 3 and comment like NP equal to 10 at NS level, LP equal to 4.
it will take care.
Anupam, can you talk over the microphone?
You can generate AB going to CD
Right.
with NP equal to 4. That means up to all NP equal to 4, all vertices, all diagrams it will take care. And
Okay.
You have to write explicitly in MATLAB. Like if
to
you
write.
do not give it the proper hierarchy, then you have to mention it while writing your MATLAB process that you need these many new physics vertices, then it will consider.
Yeah, so as they mention actually, so it also is thereafter when you actually put it in the mat graph and then want to do the computation. So if you explicitly write or emphasize that I want this new physics vertices to appear at least this order, so then it will take care in immaterial of whether you write NP comma 1 or NP comma 2 in the.
Sometimes the error is because you define two parameters with NP1 and then
Ah.
you define the Lagrangian, you put some division between the two two parameters. Like if you define lambda is equal to NP1 and also C is equal to NP1, so if you write C by lambda, it becomes order X.
Okay, so the confusion may arise by defining this C by lambda. I mean, which is NP comma 1 and which is QED comma minus 1.
No, not QED. If you define NP1 for lambda also,
Acha.
then the NP1 cancels out, so it becomes order.
No, I understand. So that's the point, that if you define both with NP1, then there might be an issue. So that's why, I mean, this lambda you define like QED comma minus 1, while for all the Wilson coefficients that you are defining is NP comma 1. So that might be the useful way. More questions? Okay, if not, then
Shankar.
Shankar.
At the beginning about like this restriction file and mask. So the thing is that while running
Okay, mic de. Ek second dara. Because we are having a recording, so it will be good to have.
So someone asked at the beginning whether what to do with this restriction file about if we don't want electrons to have masses and so on. So it depends on whether we want to use the restriction file at all. So like while we can decide not to use that restriction file altogether, in that case all the masses will be taken into consideration. If we put that restriction file, then some of the masses or widths will be taken to 0, and then we can also modify the restriction file according to our
choices.
needs.
Yeah. Okay, if that completes the questionnaire, then we would like to have the feedback form circulated to you now, where you can put your comments whatever you feel like for this particular course, and we can collect them. Okay, and yeah. Oh yeah, so there is a box you see. I mean, instead of handing over to anybody, it will be easier for you to kind of drop it over the box over there. Okay. Okay. So. Yeah. Okay. Thank you. Thank you. Thank you.
model loop will be roughly of the order of the standard model 3 contribution suppressed by the standard loop factor of 1/16 pi squared. The effective contributions from potentially 3 generated operators are necessarily to leading order in standard model processes are of order 1/lambda squared, and to compensate for that factor, there must be something in the numerator with units of energy squared. In the most favorable cases, for observables at colliders, this numerator then is proportional to some energy squared. This energy is usually larger in the collider, larger than the standard model vacuum expectation value, and therefore this is the best case scenario. There are other operators where the coefficient in front of here is the VEV squared C/lambda squared, which is smaller in general at the LHC, but for lower energy colliders or low energy effects, it is those other operators where instead of E squared you have VEV squared that are most interesting. And so this is the roughly guesstimate on the magnitude of these effects. And finally, we have the effective loop-generated operators that may contribute. And then you have an expression similar to this, but again suppressed by 1/16 pi squared. So because of this additional suppression compared to even this guy, remember this, I'm missing a factor of 2, it's 1/16 pi squared. When you compare this to this, in general, this quantity is less than 1/16 pi squared. And you have a problem observing such effects due to the sensitivity of the experiment. Nonetheless, this is the best case scenario for you, for us, to look into new physics that is not observed directly. Again, this is for the case of new physics is weakly coupled and decouples. Okay. Finally, the last case, these are really hard to see. I'll show in a minute, later on in the lecture, an example with these operators, the effective loop generator operators, actually have an interesting or potentially relevant effect. But as I mentioned repeatedly in the past, those are very rare situations. In the most general case, these things can be just dropped. Now, some of the limits that you can get from the data are extremely strict. So, for example, the limit of the operator EEDD, you can get it from in the particle data book, is lambda greater than 10.5 TeV. This is rather sad because there is no way we're going to build a 10.5 TeV collider in the near future. The LHC, I know it has, 13 TeV or whatever it is in its data. That is not the relevant energy. Remember that the LHC is a proton-proton collider. You're talking about the proton energy in the specs of the collider. What we're interested in is in the center of mass energy of the hard cross-section that involves 2 d quarks. So the momentum carried by the quarks in a proton is much smaller, on average, than the total momentum of the proton by a factor of 6 or so. And so in order to probe this type of thing, we need a very high energy collider, 60 TeV collider. Okay? So that's not going to happen in the near future, and so this looks rather despairing. But let me point out a couple of things. First, the scale associated with a given operator doesn't have to be exactly the same scale as associated with a different operator. They can be generated by different kinds of new physics, and therefore the scales can be different. I just wrote the same lambda for convenience, but that's something to keep in mind. So the limits you get from an operator that has EE and DD need not be the same scale associated with other for Fermi operators or with any of the other operators in the list that I showed you a couple of times before. So that's one thing. And the second thing is that this assumption is based on, I'm sorry, this result is based on the assumption that this is generated at tree level. As I mentioned, there's a way of ensuring that even this operator is generated by loops. And if you imagine, again, and I'm just reviewing what I mentioned, that if there is a new symmetry under which all heavy guys transform non-trivially, but all standard model particles transform trivially, then all dimension 6 operators will be generated by loops in this type of new physics scenario. And these limits get all reduced typically by a factor of 4 pi, 10. So the limit in that kind of new physics scenario would correspond to a physical scale of the order of 1 TeV, which is readily accessible to colliders and current collider, the LHC, and it certainly not doesn't mean that we will not be able to probe it. So with this kind of situation, we have a little bit of hope. Dimension 6 operators, there are no tree-level generated operators, and the above limit becomes, as I said, of the order 1 TeV. It's still high, but then there's hope. Questions about this before I go into specific applications? All right. So, realizations. I already mentioned one of those. Models that have this symmetry built in. So supersymmetry has R parity, where all the superpartners are odd and the standard model particles are even, where the standard model now denotes a two-doublet scalar model. That means the scalar sector has two doublets. And in that case, all the effects from the superpartners will be loop generated, and their constraints are correspondingly weaker. Another example, which is now less mentioned, is the case of universal higher dimensional models. And the symmetry is completely different, and I'm just putting it because it's so completely different. In this type of models, you imagine that space is 5-dimensional or higher, and the extra space-time is 5-dimensional higher, and the extra dimensions are compactified. In the simplest case, you have 5 dimensions, one of which is a circle. And the symmetry in question corresponds to translations along the compactified directions. So the heavy guys transform non-trivially under those translations. The light guys transform trivially, and then you have the same situation precisely. So this doesn't ensure that that SUSY is a perfectly viable theory, nor this, but it only ensures that some of the constraints are weakened. Okay. There is, and again, all these things have been referred to weakly coupled new physics. And because you have strongly coupled physics, then power counting is different, the limits are different, and there's certainly space for strongly coupled models. I'm sorry, models with strongly coupled new physics. All right. Any questions before I go into specific model? Okay, so what I want to look at is, in the same spirit as I mentioned of looking for one type of effect where the standard model is very suppressed or absent, that is, that it's forbidden or very suppressed within the standard model, I'm going to look at lepton number violation, the EFT. As we learned earlier, there is a single dimension 5 operator that does this, and it is defined in terms of this capital N, where capital N is this composite operator 5 transpose epsilon 5, where epsilon is I sigma 2. There's the freedom of arranging, of having flavor labels with these guys. That corresponds to the flavor label of the left-handed guy. And the reason I've chosen this n to write it like this is that in the unitary gauge, when you expand this, the n becomes a VEV times the left-handed neutrino plus other terms. So this is like a neutrino term. It involves only the left-handed neutrinos. It gives a mass to them, the Majorana mass, with very important phenomenological implications. But I want to consider other possible left-handed operators that involve, lepton number violation operators that involve leptons. But the leptons come in a left-handed variety on a right-handed variety. Left-handed are gauge doublets, the right-handed are gauge singlets, they have different hypercharges. And so the fact that we have a O5 whose scale is large, and it's large because this contributes to the neutrino masses. The neutrino masses are teeny, and the only way you can make the effect small in this is either by assuming really very, very, very small coupling, C, for this guy, or by what people believe is more natural, having a very large scale in the denominator. So I would like to examine the same type of argument as regarding the magnitude of the scale for fermions, for lepton number violating operators that involve fermions of other chiralities. So let me consider first the case that you have a left-right operator involving leptons. This is of this form. And I'm not going to go through all the details. The game in constructing the operators of this sort follows precisely the same lines as the one I followed constructing the dimension 5, in order to ensure that that this is a singlet. You have to have this result. And then the dimension of the operator is this. You want to ensure that these guys have opposite chiralities. In fact, that's why I wrote it like this. And you need an odd number of gamma matrices, and C is odd in order to have a matching of the Lorentz indices. And then you have this, you go through various values of C of number of derivatives and see what happens when the D acts on L or E. I mean, it has to act on something, and you have only one of it. When it acts on L and D, on L or E, you get D slash L. And using the equivalence theorem, you can eliminate it. D slash L, the equation of motion, the light equation of motion for the lepton, is D slash L plus a Yukawa term equal to 0. And so using the equivalence theorem, you can replace the D slash L by a Yukawa term. And so you can ignore operators like this, provided you include the other guys that involve Yukawa terms. If you neglect lepton masses, then you just get 0. The Yukawa terms are 0. And so when you actually work out all the possibilities, the smallest dimensional operator that you get has dimension 7, the one that involves a left-handed guy, which is buried in the N, I remind you, and a right-handed guy. And this illustrates one point that I was making, that instead of compiling the list of dimension 7 operators, dimension 8 and 9 and so on, it is more profitable to simply construct the ones that are relevant for the application at hand. Just because constructing all of them takes a long time. There are very many operators as you go up in dimensionality, and the applicability of all these enormous lists is limited. Finally, let me go into the RR operator, operator with two E's. And so, by the way, this I did not mention, but this operator, I'm not going to prove it, but is a potentially tree-level generated operator. Okay, so there is a kind of new physics that generates this friend here at tree level. Now, operator with two E's. Then the same story, you have to have this. For gauge invariance, this is the U1 gauge invariance, you have to have this constraint. Then the dimensionality of the object that you get, again, is of the form 2A plus C, where A is this, and then C is this, and B is related to A by this constraint. Because you have the same chiralities, you need an even number of gamma matrices, otherwise you get 0, and therefore this quantity here, this integer here is even. The smallest number that you can try is say equal to 4 of these guys, none of these guys. And then various considerations. You cannot have C equal to 0, but then you end up with a term like this, which vanishes identically because epsilon is this and is antisymmetric. And so when everything is settles down, you end up with one guy, and it's this dimension 9 operator that involves, as I promised, two right-handed leptons. It violates lepton number, and it has this coefficient here. It has dimension 9. Before I go into applications, but first, are there any questions about this? Yes?
Is there any reason this left-right, in case of the left-right operator, so you have taken this lepton mass 0?
Miss what?
This one, this lepton mass.
Oh, I just put it, why did I neglect what happens if you don't neglect lepton mass? You get the same operator. Okay? You get the same operator. I just, this is the only possibility that I could find, let me put it that way. I set it to equal to 0 because it just simplifies the discussion at this point. Yeah. Other questions?
Hello. So, I don't understand that why dimension equals to 2A plus C, that thing has come.
You don't understand this?
Yeah, dimension equals to 2A plus C in the last.
Okay, there's that, okay, so you understand this part, 3 plus A plus B plus C?
Yeah.
The 3 comes from the 2 fermions, and then this has mass dimension 1, 1, 1. So that's A plus B. And then I put B equal to A minus 3 from here. This is required by the U1. You see, this is supposed to be a gauge invariant object. So the hypercharges must add up to 0. And this is this constraint. A minus B is equal to 3.
Okay, like using this constant we are getting.
And then I just plug this in here. Sorry, keep pushing the wrong button. I plug this in here, I eliminate B, and you get this. Okay?
Yeah, got that.
Other questions? Okay, and you get this. For our case, questions about this guy. All right. Now, one of the things that I talked about is whether, I think I mentioned briefly, is how fundamental, in a way, is our dimension 5 operator. And in the sense that there are very simple new physics that generates it. It's completely classified at tree level. But at higher loop levels, and the sky's the limit, really. There's many options for generating this dimension 5 operator. And generating it by loops might have certain advantages. So the fact that your theory has, or a type of new physics theory exhibits this operator, does not mean that the scale is very large, because this operator could be generated by loops, potentially tree generated, not necessarily tree generated. So one of the examples that might be useful to look at is what happens if you have this type of new physics, a new physics that generates this guy, and it does so at tree level as it can. This is a PTG operator. And you want to look at whether it can generate or not our friend, the Majorana neutrino operator. And the answer is that it can generate it. It can generate it. I'm not going to go through the calculation in full detail, but what you have from this guy is a complicated object, has many terms, right? There are fermions, and there are two scalar doublets, and then you have vector bosons buried in it. So there are many terms in here. So you can have, in order to generate this type of neutrino masses from that type, the neutrino mass term from this type of guy, you end up somehow you need to somehow convert your E's into neutrinos, and that involves a W, and you need two W's, one for each of these guys, and you somehow you don't want any W's in the external legs, because the neutrino mass term has just two neutrinos. So what happens is this. You end up with this is my operator here, and I use these guys to have a W both of them, and then I have my two electrons here, and I have an electron here, and then it's a two-loop graph, and then you generate a neutrino W. This would be the electron and the electron. But there is more. The neutrinos there's more, and you should have complained, as you would if I give you time to do it. But there is something wrong in this diagram. So what's wrong with this diagram? Where am I lying to you? Faculty are not allowed to answer. Any guesses? Where am I lying? It lies in the internal structure of the standard model. It's a pure standard model. Let me put it more. This vertex is highly problematic, as is this. Why? No? Go. Yes, sir? Say again. Lepton number. No, not Lepton number.
The E is singlet.
The E is a singlet. Who gets the prize? Hey, oh big. Yay. Thank you. The E is a singlet. I didn't just write E because it's an electron. I wrote E because it's in here. It's a right-handed field. And the neutrino is left-handed. W doesn't change chiralities. This vertex ain't there. I have to do something else. Okay? So I have to somehow introduce a chirality flip in the thing. So there's going to be a chirality flip. And the reason I go into this, through this thing will become clear in a second. It's not that I'm just trying to needle you. I'm going to put the here. So I'm going to put the chirality flip here, another here. This is right, it becomes left. Okay, so why is this of use? Even though you have here a two-loop graph, so it's suppressed by 1/16 pi squared, the magnitude of this thing tends to be very large compared to data. So you have a problem. Even if you say the coefficient of this guy is C, and it's dimension 9, so it's divided by lambda to the 5, I think. And you have C lambda to the 5 from the operator, C lambda to the 5. And then I have 1 over 16 pi squared. And I want, because I'm looking for low energy, low scale lepton number violating effects, I want to say this thing, the order of TeVs-ish. Okay? And yet I want the neutrino masses to have the right magnitude, you know, the order of what is 10 to the minus 3, 10 to the minus 2 electron volts. This suppression is just not enough. But with the added factor of the chirality flip gives you which is very small also. And with it, you get enough suppression to accommodate relatively low scales lambda and the tiny, tiny, tiny neutrino masses. There is a name for this type of argument. It basically says that if you have a type of lepton number violation, you will generate all types of lepton number violation at some loop order. At some loop order. At some loop order. You can go through the same game with the left-right operator, and you can see how it goes. You already have one left-handed guy. The other one you will have to transform into a left-handed neutrino using, again, one chirality flip. So in that case, for dimension 7, you have a suppression of lambda cubed. You have a 1 over 16 pi squared, only one loop, and only one factor of the chirality flip, which allows lepton number violation at largish scale, 100 TeV, 100 TeV, where dimension 5 allows, allows lepton number violation scales of the order 100 TeV, and in that case, such that they're consistent with the neutrino mass scale. Yes, sir.
So, don't we have one wave to the power 4?
One
Wave to the power 4.
d to the power 4?
Wave.
Bev.
From the scale.
Oh, the actual scale. Yeah, no, I'm just giving you the suppression factors. For the neutrino masses, you have to have V cubed, V fourth, V6, sorry, to get the, so that the mass is a mass. Okay. So, other questions? All right, so the point is that when you see operators like this, if the argument that this is generated by scales of the order of 10 to the 15, 16 GeV is true, provided you require this thing to occur at tree level. But there's other kinds of new physics that generate lepton number violation at tree level, but not here. Say here. And it feeds up or down or sideways, whatever you want to say, and generates this guy, but at sufficient high order in the loop expansion, and with miraculous or fortunate, if it depends how you see it, fortunate suppressions of suppression factors, which are not fine-tuned or accidental in any way. This is just the way nature works. That you can accommodate operator of this type with a very small coefficient while having operator of this type with coefficient of order 1. Okay? Questions? All right, next application. Neutrinoless double beta decay. So this is my excuse for doing neutrino, for the title of neutrino physics. I'm going to look at a process that has no neutrinos. So neutrinoless double beta decay is a particularly fortunate process in that it allows us to probe lepton number violation at low energy. And so, as you know, or should know, many nuclei go, I said some nuclei, but actually quite a few of them undergo what's called beta decay. In the beta decay, the neutron decays into a proton, electron, antineutrino. I think Shuba talked about it a couple of discussions ago. There are such nuclei, but there are other nuclei that have a peculiarity. It turns out that if you imagine one proton decaying, the resulting nuclei would have a heavy, okay, so what happened? One neutron decaying, have a nucleus. The neutron decays, and it becomes a proton, spits out an electron. And so the charge of the nucleus increases by 1. So in a beta decay, Z goes into Z plus 1 in the nucleus. So it could happen, and it does happen, that in certain nuclei, the energy of the binding energy of a nucleus with charge Z is larger than the energy. I got this backward. Sorry, it's stupid. That the energy of the Z nucleus is smaller than the binding energy of Z plus 1 nuclei. This is backward, sorry. So that it just cannot decay for energetic reasons. That decay cannot happen. And however, if 2 neutrons decay, Z goes into Z plus 2, and the new nucleus has a lower energy, so this goes backward too. And the result is allowed. And I cannot change it because this is a PDF. So apologies. I cannot put my PowerPoint because the machine doesn't read this font. Now, this type of situation where a single beta decay is forbidden and a double beta decay is allowed is not infrequent. All these guys here that I've listed here are subject to this type of process. Some germanium atoms which are useful in experiments. Our friend U-238 and so on does that. But in all those cases, what the standard model predicts is the production of 1 for beta decay or 2 for double beta decay neutrinos. In this case, antineutrinos. But you could imagine situations where new physics produces a very rare decay where somehow these neutrinos just don't show up. Of course, the physics that produces such a thing cannot be the standard model. It just doesn't happen in the standard model. Lepton number is conserved except for non-perturbative effect, tiny non-perturbative effects. So the Gerda experiment is the latest in a long series of experiments that look for the possibility of having a decay, in this case of a germanium atom, into a nucleus, into 2 electrons. So the thing produces 2 electrons, transforms into a nucleus with a charge plus 2, and produces no neutrinos. So this is what this means, no neutrino, double beta decay in germanium. And so far, there is no indication that this occurs. So we have a limit on the lifetime of about 2 times 10 to the 26 years. There was some years back a paper claiming, from a well-respected experimentalist, claiming that a signal was observed. But I think that turned out to be a false hope. It didn't bear scrutiny thereafter. Okay. So this is the best thing we have, limit. And we can use this data to put limits on the various possible lepton number violating processes, operators that you might like. Because because the game here involves electrons, because it involves electrons, in particular leptons, is the motivation for me to look at dimension 7, 9 operators that involve leptons and violate lepton number, because this is the process I want to apply them. So I had this in mind when I constructed the dimension 7, dimension 9 operators. People have been playing with the dimension 5 operator for these guys for a very long time, for a very, very long time. So I'm not going to talk about that. That's a long story. For this case, for the dimension 5 operators, you can have this result. Ugh, I need more space here. You have a quark, and it spits out a W, and this guy spits out the W2. Okay, and in normal beta decay, double beta decay, the W gives out an electron and an antineutrino, and the other W gives another electron and another antineutrino. And then you had neutrinos double beta decay. This is part of the initial nucleus. This is part of the final nucleus. And you have 2 electrons. So neutrinos, that's the neutrinos double beta decay. But if you have a dimension 5 operator interaction of the type listed there, you're allowed this vertex. Well, this guy here is precisely this. That has a neutrino, well, this is the conjugate of this guy. Nu bar, C, nu bar. So you can have this process where you start with a nucleus with charge Z, and Z plus 2, you spit out 2 electrons with no neutrinos. And people consider this extensively. I want to consider alternate possibilities of new physics that generate the same final state, but with different underlying physics. All right. So this is what I just wrote down here. If you have an electron chirality of this form, the diagram, which is the same here in detail, that generates the neutrino double beta decay process is this. This is the dimension 5 operator. Okay? And the amplitude is of order in the scale. The amplitude looks like this. This is just a very simple estimate. Q is the momentum transfer along the W. So it's a very simple expression. Then the amplitude looks like this. It's a hand-wavy estimate, but useful, with a factor on top of it. And if you, the factor A is what contains the new physics coefficients. So in the case of neutrino, the dimension 5 operator, A is simply V over lambda. For the left-right case, that is when the electron chirality is different, one is left-handed, the other is right-handed, the relevant operator is this guy. Then A becomes an object of this type, this expression, with Q over V here. And the right case looks like this, and you have a substantially different, actually different factor on top of this common denominator for all cases. This is again with the assumption that this guy's generated at 3 level, this can generate, okay? having the amplitude, I can translate that into a lifetime, and from that and this limit, I can put a constraint on lambda. I've set c equal to 1. Okay. C equal to 1 in that case. All right? And it's, this is a recap of this thing. The implications depend on this type of physics. The amplitude, again, this I'm repeating what it is. What epsilon is V over lambda. Eta is Q over V. For the type of nuclei that we're looking at, it's about 2 times 10 to the minus 4. The limit from the experimental limit, the limit on A can be translated. You see, the relation between the amplitude and the lifetime is a known factor. Between the amplitude A, the amplitude and A is a known factor, and therefore the relation between the lifetime and A, it's again a known factor, not something you're going to put a bound on. This is a quantity you can estimate. And so what you get is you can translate the limit from the experiment into a limit on A, which is this, and then you use the expression for A as 1 over lambda cubed, 1 over lambda to the 5th, with additional suppressions to extract a limit on lambda. So if you have a dimension 5 operator generated at tree level, A is epsilon, and the corresponding scale of new physics is at least about 10 to the 11 TeV. Very large, 10 to the 14 GeV, it's a large scale. It is consistent with having small neutrino masses, roughly. I'm not doing into full detail. Consistent with small neutrino masses. If you go to the case where one of the leptons is left-handed, the other is right-handed, and the amplitude of A has additional suppressions, powers over lambda, and additional suppression of eta. And that reduces significantly the scale of new physics that can accommodate this constraint to lambda of at least 191 TeV. It's significant reduction, but even 200 TeV is completely outside the directive, the possibility of probing directly at a collider in the near future. Finally, dimension 9 operator has even more suppression, another factor of eta, 2 powers of epsilon, and that again reduces the expected minimum scale of new physics that can accommodate this limit to about 3 TeV. Now this is at the edge of what the LHC can do, but still, maybe with enough statistics, it can probe it. So the lesson for this is that higher dimensional operators can have interesting effects, and these effects can even be measured if the precision of the experiment is sufficiently high. Well, we haven't measured it, but at least we have put a bound on them, provided the experiment precision is sufficiently high. Another very high precision experiment is G-2 of the muon. That's another one. I will not go through this, but there are a certain number of operators that contribute to G-2, and you can put a limit on the limit on the scale of new physics for using the data from that experiment. For a while, there was a discrepancy in that experiment between G-2, between standard model prediction and observation. That, I think, has become controversial since, unfortunately. And so then the hopes of having an unambiguous new physics signal that involves a controlled tabletop or a controlled experiment here on Earth have dwindled a little bit. But even in that case, you can do exactly the same process, go through the same process. Look at G-2, find the operators that can contribute to it, and make this type of estimates. You can consider going to, this is not a Lepton number violating process at all, it's just a process. consider the limits that you get from such an experiment, or from the data from G minus 2. Again, if the discrepancy between that and the standard model is resurrected, then we will have a way of identifying, perhaps, the most promising operators that can be responsible for the effect, for the new physics effect, the deviation from the standard model. So suppose somebody finds a limit, not a limit, but the value for this. I don't know, 10 to the 27 years. What happens in that case? Well, you can choose different type of models where this guy is created at tree level, or this, and examine them further. If this is created at tree level, then this will not change much. It will tell you that lambda is of the order of 10 to the 11, 10 to the 12 TeV. And you'll have to find something that's not a collider to probe it. The same thing for here. But this guy, you'll end up with 3.3 or so. It doesn't change very much in that case. And then you might ask, what kind of new physics can possibly create or generate this operator of mine? I will not go, okay, so there's several models that can create it with, that can generate it at tree level. It involves relatively straightforward extensions of the standard model. The simplest model I know it involves an extended scalar sector where either lepton number is broken softly or spontaneous. Two things. But the models are conceptually very simple and so on. And so the idea is, if you have data, not just limits, but data that indicate that the coefficient of operator like this could be non-zero. I said could because, in fact, it could be this guy here, right? That's generating the thing at tree level. But this could be non-zero. Then you can reverse engineer this operator and find the type of new physics that could be responsible for generating this at a scale of, say, 3 or so TeV. And then you tell your collider friends that there's promising models that can generate the observation of neutrinoless double beta decay, in which they can confirm or exclude model by model at the LHC. So it's an involved process, but life is complicated at this level. Okay, life is complicated. Questions about neutrinoless double beta? Yes.
So in this case, in this model, we had this bound on this lambda. New scale is the decreasing. Basically, when the dimension of the operator is increased.
Dimension of the operator is integer.
Dimension of the operator.
Yes.
5 is the 10 to the power 11, 7 is 10 to the power 191. In case of the 9 is 3.2.
Yes.
So suppose when we are thinking of a model, so because the model testability is very important. So in future this model is observed or not depend on that. Suppose if the 3.2 is the LSC, suppose if it is possible in the LSC, because LSC is the root S is 14. So my question is, suppose what kind of model we can first thought? Suppose is dimension 5, next dimension 6, dimension 7, or because this the card is start from the higher dimension. Suppose 9 is the 3.2. So if we start from the higher dimension, suppose 9, then 8, then 7, like that. So which way is the best?
So the question is what?
Question is basically operator. Suppose we start from the lower dimension to higher, or higher dimension to lower.
Okay, my preference is, since the scale of this guy is 10 to the 11, this is not going to be observable at the LHC, nor is this, the 191. The dimension 9 is the first type of operators that generate, presumably there's a dimension 11 operator that does this at even lower scale, but I didn't have the strength to construct a dimension 11 operator or operators that contribute. But the idea would be to tell your friends at the LHC that you have a promising model that accounts for the recent Nobel Prize winning observation of non-zero neutrinos double beta decay, and which they can probe at the LHC by doing this and this and that. Okay, and I think that's the idea, that's the logic. But for that, you need to have an indication that this is actually the case. Otherwise, you can tell, I mean, the people at the LHC might test it or not, but it's just a model that might have some interest, but, you know. Other questions? Okay, next application. Next application, and I think I'm going to spill over into next session with this. So next application is a study of the Higgs physics that I'm not going to go through it in full detail, but I will try to give you some pointers as to where some interesting effects occur. So one of the things that colliders, the LHC, can measure are the various couplings of the Higgs to vector bosons, to quarks and leptons, and also at one loop level to the photon and to the gluon. And I didn't put in here, there's another corresponding coupling of the Higgs to a photon and a Z. The standard model predicts a tree level with certain amplitudes that are proportional to the masses of the fermions. Not so for the vector bosons. It's proportional to the masses of the vector bosons, squared, like that. Okay. For the case of the coupling of the Higgs to the gluons and to two photons, and to the photon and the Z, the process is a one-loop process, as indicated here by this funny parametrization. So you might say, I've been telling you that there's a 1/16 pi squared. That is true. So the pi's are hidden in alpha, which gives you a 1/4 pi, and explicitly displayed in front of it. So it's in two places. But this is a one-loop effect. In fact, this guy is very much in evidence just by the fact that we see the Higgs. The main production of the Higgs is through gluon-gluon fusion, as it's called. Glue goes into Higgs, and then the Higgs does its own thing decaying. The reason why that particular process, even though it's a one-loop process and much suppressed in the standard model, is important is due to the enormous gluon luminosity at the LHC. The LHC has a lot of gluons, a lot of gluons. So luminosity makes up for the loop factor suppression that this amplitude has. Okay. The case of the photons, which was one of the modes by which the Higgs was discovered, is again a one-loop process. And again, you say, well, gee, that's very tiny. Indeed, it's true, but the signal is very clean. So though it took a while, the LHC could identify glue-glue, Higgs, photon-photon, which you count. It's a two-loop process in the standard model. Very rare. Very rare. I don't think it's properly recognized the exquisite precision the LHC has reached in order to do this kind of thing. No other science cannot come even close to this type of precision when measure anything. In this case, high energy physics is just about the best. If you want to consider deviations from these couplings, then one way of doing it, one way of including it, it's not the only way, but the one that is often used, is to replace these couplings by adding an unknown to be determined factor. When I wrote this, the common letter for that factor was the letter C. But that got replaced by kappa, for good reason. Because for the case of W, it would become CW, that is easily mistaken with the cosine of the weak mixing angle and therefore causing unnecessary confusion. Okay. So, unfortunately, I'm going to keep the C. So CW is not the cosine of the weak mixing angle. It is an unknown constant. The experiments measure or constrain the CIs. Actually, they measure them. And what they find is that all one. I mean, that's basically what has happened, okay, within experimental accuracy. But I need to relate those couplings to CO. And part of the exercise will be to go and find the operators that could generate HWW, HZZ, and so on couplings, and expressing them as HWW times something, and then relating that something to 2CW and W squared over V. I mean, that kind of thing. But I will not do this right now. I will go first. I will just finish right now by telling you that the relevant operators can be divided into three groups, either pure Higgs group, this guy, or operators that affect the HW and HZ coupling, this guy, and finally the couplings, the one that affects the coupling of H, Z, and W to the fermions. Okay, so it's a little bit more extensive class than you would think from here, that just HWW, HZZ, and so on couplings. Now, for the matching of this notation to the effective theory notation, I'm going to have to consider a slightly larger set of operators. So what I will do briefly is go through one of these cases in a little bit of detail, and then mention the other, how it goes, so it's not too repetitive, and then show you the conclusion. Okay, that will happen later on this afternoon. And after that, I will go briefly and talk about my version of effective field theory when applied to dark matter. Okay. Any questions? Okay, in which case we can all go to lunch, and I hope to see you this afternoon. Thank you. All right, welcome back to the last session of the course from my part. Let me remind you briefly what I was talking about when we stopped earlier today, which is looking at possible new physics effects involving the Higgs. And here, these are not the only possible effects involving the Higgs. Those are the ones that change the coupling of the Higgs to the standard model particles. And as I mentioned, this is parameterized by this series of constants that are called C sub W, Z, and so on. And and these are the things experiments tend to measure. And I'm going to look at these things a little bit, trying to express them in terms of the Wilson, as it's called, the coefficients of the effective theory, C sub O, and make some comments along the way that I think will be illuminating in considering which of these effects may be or may not be large. You notice that I did not include couplings to the up and down quark, to the electron and the muon. The reason for that is that these are expected, well, in the standard model, they're very small. They're proportional to the corresponding masses divided by the vacuum expectation value. So very small. And since we don't see any corrections to the standard model effects at low energies and at the LHC, which involve these electrons, muons, up and down, charm and strange quarks, they are not included in here. In principle, this can be extended to everything, at the LHC, these are the things that have a chance of being measured. So I mentioned that the operators that come into play in this exercise can be classified into these three categories, and I'll go through them one by one. So let me first go to the pure Higgs operators. These are two of them. There's two of them, simply. This guy and this guy. Now, when you write down the Higgs, the scalar doublet in terms of the Higgs and the vacuum expectation value in the unitary gauge, you replace phi basically by, you replace phi by this expression. And so when you add this object here, this first one, to the Lagrangian, what you get is a term that goes like the standard model that includes a term that goes like 1/2 dh squared. This is the standard model piece. And then when you put this thing here, it generates, among other terms, this object, epsilon c d phi squared, where epsilon hereafter will be v squared over lambda squared. When you look at this thing, this object changes, among other things, the mass of the Higgs, the Webb, and many other things. This I will not talk about, because this doesn't involve the couplings of the Z, of the Higgs to the fermions. But this does, because in order to have a properly normalized kinetic piece, one needs to do a finite renormalization. That is, instead of considering the little field H here that comes up here, we should consider this field instead, that we'll call capital H, the physical field, which is related by a factor with a little h. So what one has to do to take into account the presence of these operators is replace little h by big H everywhere. Okay? So that's one effect that, that one must take into account. So this is it. As I mentioned here, phi to 6 changes V and can be absorbed in finite renormalizations. This can be proved only by looking at Higgs self-interactions. Higgs triple, quartic, quintic, and sextic vertices of the Higgs are generated here, but those are not they're not the ones that we're talking about. So not interactions we're talking about here. And so I will not talk about this guy. I don't have to talk about this guy. What is important is that what this does is change the canonical normalization of the field. And in order to return to a properly normalized field, one has to replace little h by h everywhere. That's it. That's what this field, the pure Higgs operators do. Any questions? Okay. Second group. These are operators that modify the couplings of the Higgs to the W and to the Z directly. In fact, there's only one of them that is generated among all the PTG list, and it's only this guy. This guy indeed does modify the coupling of the Z, the coupling of the Higgs to the W and the Z, but it does something else also. It changes the vacuum polarization of the Z, and so without affecting the vacuum polarization of the W. Therefore, that makes a change in the canonical relationship where it says that W is the mz times the cosine of the weak mixing angle. That relationship is modified by the presence of this operator. And the difference has a name, is the oblique t parameter. In the standard model, the oblique t parameter is 0. And the tree level. And therefore, this operator changes that. Instead of being 0, it is this thing. This is a subindex. So this is C sub phi d, like there. C sub phi d times epsilon, which I remind you, it's v squared over lambda squared, and divided by alpha. And that alpha shows up because of the definition of what the oblique parameter is. And so in the standard model, this is 0 tree level. And it's been very precisely measured. When I last checked, it was the order of 10%. And what happens then is that because of these constraints, the effects of this operator on the Higgs couplings, now on the Higgs couplings to the Z and W, are too constrained. That means, what I mean is, they are required to be very small, too small to be distinguished from the noise given the precision of the LHC. So this operator can be ignored just because this constraint ensures that its effects are below the LHC sensitivity. And I'm going to do this several times. If a collider or low energy experiment or whatever data implies that the coefficient of an operator is sufficiently small, I just drop it. I will not talk about it anymore. Not because it's not interesting in general, but because at least currently the effects are known, because of this constraint, to be below the LHC sensitivity. The rest of the operators that that connect the Higgs and the vector bosons, all these guys, are loop generated, and again, they can be neglected to a first approximation because they have this inherent suppression. Therefore, the conclusion is that the HZZ and HWW couplings will be standard model to lowest order. Any questions? Okay, we're done with group number 2. Let's go to the last one. Now there's the coupling of the W and Z to the fermions. There are many. These guys that have this derivative to the leptons, to the quarks, and then this extra guy that couples to an up and down with a charge conjugate doublet here. All these, if you expand them, this guy, they generate a term that goes like fermion Z slash, the Z field, fermion. Fermion Z slash fermion. Similar here. Here generates up W slash D. What that means is that all these guys do is modify the coupling of the fermions to the Z and the W. But those have been very well measured by LEP, and by LHC, to the point that the constraints require lambda to be greater than 1 TeV in all of them, except for the top quark, And they lead to only 1% corrections to the standard model, or smaller, and they are again below the where the measuring these couplings to 1% is certainly not below the LHC sensitivity. What is below the LHC sensitivity is the effect of such 1% corrections would have in the Higgs couplings. Okay, so that is what's going on here. The effect of this on the Higgs couplings to the various particles is it's not precise enough, those measurements, to be able to detect this type of effects. So all these guys I can drop, except for the top. Again, let's note it here. And the loop-generated guys are, again, too small. They will have an inherent suppression factor, and I'll just drop. Any question? So the last set. So the H coupling to fermions, scalar coupling to fermions. These are these Yukawa-like couplings. This is the standard model Yukawa coupling multiplied by phi squared. That's what they are. In unitary gauge, this object, phi squared, and I forgot to divide by lambda squared, I apologize. So this is phi squared over lambda squared is epsilon over 2v plus 3h plus blah, blah, blah. Okay, let me write down this. So phi squared over lambda squared is epsilon over 2 v plus 3h plus blah, 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 blah. So what does this guy do? This guy modifies the mass of the electron, or the Yukawa coupling of the electron, and of the fermions. So the whole Lagrangian contains a term that goes like this. Yukawa, and I'm going to just look at the generic fermion. You have something like L bar E phi. I'm sorry, I used the wrong phi. Phi. Okay, L E phi plus this guy plus C over lambda squared phi phi squared L bar E phi. So let's see what we get from this exercise. What we is the following. So we get y plus epsilon v I think I made a mistake. I'm sorry. It goes like this. Epsilon over 2 v over root 2 times L bar, actually, sorry, that goes like E left, E right. This is what we get for one term. And, I'm sorry, it goes like here. Sorry. And then we have another term that involves the Higgs, and that is y plus epsilon over 2 times 3 and h over root 2 e bar e. And there are other terms. So this can be absorbed in a renormalization of y. You just shift y. But when you, so this disappears, and so you get the standard expression for the mass of the electron. But when you do that shift, you cannot then eliminate this guy. You can absorb, if you wish, 1 epsilon over 2, but 2 remain. And so there is a shift in the coupling of the Higgs to the fermions. In addition, I have to replace little h by big H. So, so there is some modification to the coupling of the fermions, and therefore I must include these guys. Okay, these are not necessarily as well measured as one would like. Because, I'm sorry, the masses are very well measured. This coupling is not very well measured. The one of the Higgs to the fermions. In fact, that's one of the goals of the LHC. Finally, let me look at some loop-generated operators. Because, as I mentioned, some of the most interesting processes involving the Higgs, well, and necessary processes, like the production of the Higgs, involves the HGG, gluon-gluon coupling, which is loop-generated. And because of the interesting decay of the Higgs to 2 photons and to Z gamma are also loop-generated, then effective operators that are loop-generated themselves that interfere with the standard model will be, in principle, will give, in principle, a large enough effects that that can be measured or constrained given the LHC sensitivity. Because we're comparing apples with apples, the standard model is loop, these guys are loop. And the interference term goes like 1 over lambda squared, and we're good. The terms that are loop generated and can be ignored are those that do not interfere with the standard model, because then their effects are 1 over lambda to the 4th in the cross-section, because the cross-section is square of the amplitude. There is no interference term that would give a 1 over lambda squared. And in addition, they have a 1 over 16 pi squared suppression. So these we will ignore. And in particular, those are the ones that include x tilde, where x tilde is the dual of the corresponding field strength. Okay? Questions so far? All right, so let's see what we get. So the phenomenology. So the coupling of the H to 2 fermions, well, it's related to by kappa or C. I changed to kappa because C became now very confusing. Kappa squared of the standard model value. And in our case, kappa squared, if you do everything carefully, is this thing. This comes from the renormalization of the Higgs, and this comes from these operators such as the ones here on the board. You can also calculate the Higgs to VV star, that is producing a physical Z or W and a virtual Z or W thing, which was one of the discovery modes of the Higgs. And you see that, in fact, this, as I argued, this vertex here has to be standard model within the precision available. This also, this also, this also, and this actually is very small for the same reason. And I'll come back to this in a second for the same reason. And therefore, this is affected only by the wave function renormalization of the Higgs potentially. All the other effects are there, but they're too small. Why is this guy very small? I'll tell you. The reason is that this comes from this vertex here, Z8, because these operators, I told you, I'm going to go back to the board. I told you they generate modifications to the coupling of the Z to the fermions. But they do more. So when you have an operator like this, D back and forth, phi dagger, fermion, gamma mu, fermion, and you expand in the unitary gauge, you get a term that goes like V squared, psi bar, Z slash psi. But that's not the only term. That term comes from replacing these guys by the web. You get other terms that go like V squared, H, psi bar, Z slash psi, and things like that. In many other terms. Pardon me? Yeah, the H over V. Sorry, yeah. You get this term, and many others, or several others. There's like 4 of them. There's several others. Okay, so what I'm telling you is what Lep constrains is this guy, this coupling. So the coefficient of that guy, of this full operator, is constrained by the Lep data and by the LHC data, the coupling of Z2. And therefore, since it's a coefficient for the whole operator, so will be the coefficient for this operator. And therefore, if this is small, this has to be small because it's the same coefficient. And therefore, I can drop these guys. And this is the only quantity that's measured. Lastly, there is the coefficient, the modifications to the 2-photon Z gamma and GG couplings, and you get this horrible thing. Why? Because of various loop effects that you take into account. The standard model, this comes from interference between the standard model and the effective theory. The standard model is a one-loop effect. And so you have to evaluate a loop. And the loop doesn't give a number like 3/2 or a nice rational number, but just numbers that depend on the masses in the loop, the top quark, the W, the G, the gauge coupling constant, things like that. And so you get funny numbers like this from that. Okay? But that is just comes from the interference terms. It's an interference term because all these things will be proportional to epsilon. Epsilon, epsilon, epsilon goes 1 over lambda squared, and that has to come from the cross term between the standard model and the effective theory. And here you have these guys. Okay, let me go back. So this is the translation of things. So why is this useful? This is useful, I should say. This is useful because in the language of the kappas, you're just measuring numbers. In the language of the Wilson operators, Wilson coefficients, you can relate those to specific operators whose underlying physics you can try to unravel. The effective operators, being gauge invariant, in a sense are physical. They satisfy all the symmetries of the standard model, and so they have that going for them. This expression that I started with is very simple, much simpler than the effective theory, but it has a problem. There is no connection between between this type of coefficients, or if you call them kappa, kappa W, kappa Z, and any kind of underlying physics. They're just numbers. There is no reason to suppose that this CW will be of this precise form in the standard model effective theory. There is no reason to suppose. What this is concluding, for example, is that any reasonable kind of new physics, to a first approximation, will give the same modification to the W and Z couplings. Something that, can be tested in principle. So if someone finds a deviation from the standard model in this type of decay for the W, H2W, W star, then the same magnitude of deviation or percentual deviation should be found in the Z decay, if this is to be consistent. This is a direct prediction of this theory. The similar for these things, there is no reason to suppose that these particular expressions will hold. On the other hand, this is a result that connects, as I said, in a way, the physical underlying theory with the coefficients that you actually measure. Notice that there are more than 3 coefficients involved here. There's 1 here, 2, 3, 4, 5 coefficients involved here. And we have only 3 numbers. So that might be discouraging. You say, well, we'll never be able to separate these guys from one another, and we'll just get limited information. That is, unfortunately, often the case. The data that we can measure relatively easily, that we can obtain relatively easily, is not sufficient to be able to distinguish all possible combination of operators. So it's impossible to differentiate between a non-zero Z gamma gamma and a non-zero C D phi, for example. But there's one exception, and that is the exception, and that corresponds to the case where all operators are loop generated. In that case, this is true. And we have certainly enough data, 1, 2, 3 data points for 1, 2 coefficients. Yeah, pretty good. And so we can put a limit on lambda based on this thing, which is 1.4 TB.
Is basically that you kill those tree generator operators by hand.
What happens is, not by hand, I choose the right model, supersymmetry. I choose the right model, not by hand, not by hand. There are models where there are no tree-level generator. And then what happens? So let me go back to this here. So see what happens here. This gamma gamma, it's tilde, came from loop-generated operator coefficients. This, by the normalization that I've chosen, these guys are from loop-generated guys. This goes like 1 over 16 pi squared. But I'm explicitly multiplying by 16 pi squared, so this in general is of order 1. Okay. And that's just manipulation. There's nothing deep in this. It's just a manipulation of the expressions. There's no similarly here. So this is order 1, order 1, order 1. And that's why, and it appears here in this combination. Now, if everything is loop generated, these guys will be loop generated as well. So whereas these guys will be of order 1, now these guys will be tiny. This will be tiny, and I can just drop it. And so when you measure H2 gamma gamma in that kind of new physics, you will measure C tilde gamma gamma. When you measure this, you measure this. When you measure this, you measure this. Is a one-to-one correspondence between data and unknown coefficients. You can start mapping out your effective theory. Okay? And that is the special case. And from the data at the LHC, maybe this probably has improved by now, because these measurements have become more and more precise as time goes on. So this is a lower limit. I don't know. But at least it's one case where existing data is sufficient to put an unambiguous limit on the...
So this is assuming that this C tilde GG is 1 by 16 pi square.
I'm assuming, okay, these guys are always 1 over 16 pi squared. Or 1 6. These guys may or may not be, depending if this is, but in the type of physics that where this is 1 over 16 pi squared, those go away. In the type of physics where they do not, then you can't tell that whether, suppose you get absolutely, measure this with incredible precision, and you find that you get exactly the standard model one. So you get 1. That doesn't mean that this and this are 0. It just means that this linear combination is 0. So there could be some cancellation. Okay? And so the point of what I'm telling you is in the case where there are no PTG operators, not tree-generated operators at all, then that cancellation cannot occur because the leading effects on all these measurements come from only 3 coefficients that don't interfere with one another. And so there's a direct correspondence between kappa and C, kappa and C, kappa and C. There's no cancellation. All right. Any questions? This is the end of the standard model application section. Going once, going twice. Remember, this is Friday. I'm not here tomorrow. Okay. Last chance. No, actually, you can always email me, please. Okay. If not, let me go to the last application that I had in mind, and this is application to dark matter physics. Now, dark matter is characterized by 2 things. We don't know what it is. We really think that it's there, but we have no idea what its properties are. But that ignorance has never stopped a theoretical physicist from speculating using prejudice, hand-waving, and sometimes rigorous arguments to try to classify all possibilities. From what I'm going to tell you, I'm going to try to be as honest as possible. It's certainly not the only possibility. It's the possibility I like. And so you have to take that into account. I'm prejudiced for it. But and nature certainly takes no account of what I like or not like. Otherwise, I would be very rich. So then the point is that take this with a grain of salt as one possible approach to the effective theory to the case of a large amount of stuff that's out there that's described by particle physics, okay, about whose properties we experimentally know nothing. So as Shubha mentioned earlier in the course, the latest cosmic census of matter gives about 23% of the contents to dark matter. So this is dark matter, this is dark energy. So we know this behaves like matter. We have absolutely no idea what this is, that kind of thing. And we are here. Actually, we are in a sliver of this. Most of this thing is gas. Okay, so we are just about inside the 1% of the energy matter content of the universe. Whatever information we have about this guy, which is the one, I'm not going to talk about dark energy, about this guy, is obtained using gravitational effects, and therefore we have no knowledge about what the microphysics of this dark matter is. Could be, in fact. So there are many, many models. And when I say it's the simplest, again, it's the simplest for me. It might be very complicated for others, but it's for me. And I'm not going to write for me because it looks awful on the slide, but yes, keep it into account. Okay? So many models, the simplest that I thought of is the following. There are two sectors, us and them. And we have mediators between the standard model and the dark sector. Yeah. Okay. If the mediators are heavy compared to the scales, they can be integrated out, and you get an effective theory that generates operators like this. You get a standard model coupling, the thing mediator couples to in the standard model, and the thing the mediator couples in the dark sector, and I've integrated out, which in this simple vision, and I'm trying to consider a simple scenario, it's just kind of a propagator between this and this. So you get 1 over p squared minus m squared. I'm telling you the momentum p squared is much smaller than m squared. And so you just get m to some power. And I'm putting m to the k because what happens if it's a fermion? Then you get 1 over m instead of 1 over m squared. So that looks familiar. I mean, it's just another effective operator. So I will assume the following things. All dark matter couplings to the standard model are, all dark matter particles coupling to the standard model are non-singlet under some group GDM. That is, they couple via the mediator. So any part of the dark sector, could be all the dark sector, but any part of the dark sector that actually participates in this interaction transforms non-trivially under some group GDM. There are many choices for GDM. Doesn't matter. Many choices. You can choose Z2, it's very common. You can choose a gauge group. That's also common. It doesn't matter. Just a gauge. I will not need to specify. The dark sector has particles of spin less than 1, but I will not. I will assume that an antisymmetric tensor field, which also describes spin 1 particles, is not there. A prejudice. The reason is I don't know how to write Lagrangians with this guy, so I ignore it. And I also assume that the mediators have spin less than 1. But again, no antisymmetric tensor field exchange. So the strategy I will follow is to construct the leading, that is, as low-dimensional and tree-generated standard model dark matter interactions, infer the types of mediators that can be involved, find all the standard model interactions generated by each mediator, and construct then a UV complete theory. I will not get to this part. I will just sketch it at the end. So the first thing to do is construct the leading tree-level generated lower dimensional SMTM interactions. And for that, I need to list these guys, this and this guy, in increasing order of dimension. Notice that even though I'm assuming that these guys are, I didn't write, I will assume also that the dark matter particles are singlets under the standard model gauge group. So that's a fourth assumption that I did not list. So these guys, I just need all gauge invariant standard model operators, but I don't have to assume that they're Lorentz scalars. That's not necessarily true, because the mediator might not be a Lorentz scalar, might be a vector, might be a fermion, but they also may be a scalar. So I need all these guys without the assumption that they're scalars. And similarly for the dark matter guys. Okay. Symbolically, the Lagrangian looks like this. You have P, which is the mediator, SM, P, dm, plus LP, the mediator. Fields are assumed to be singlets under both the standard model symmetries and under this guy, GDM. And they have some Lagrangian between them. And so you have this kind of thing. This would be OSM, this ODM, and you get OSM, ODM divided by some mass here. So when you square this, when you consider this, because the mediator couples to SM and DM, you must get SMDM terms, but also pure standard model and also pure dark. This is inescapable. These guys can be tested at the standard model, at the LHC directly. It modifies the standard model couplings. This generates dark matter self-interactions that may be large or small depending on the details of the theory. And this represents what's called portal couplings. That is the portal through which the standard model can look out into the dark world. I am then now going to list the operators that are of relevance. The standard model operators of dimension 1, which are gauge invariants, are just none. 3/2, none. Dimension 2, there are 2. Phi squared, the doublet squared, and B mu nu. B mu nu, B is the gauge field, I remind you, of the U1 hypercharge in the standard model. It carries no quantum numbers, gauge quantum numbers. It's a gauge singlet. It's invariant on the gauge transformations. And so it belongs in this line. Dimension 5/2, you have only one. L bar, phi tilde. Dimension 3 are these, dimension 7, 2 are these, and you can amuse yourselves going back. Okay. Now, in constructing the dark matter operators, I'm going to assume that I have a generic theory involving fermions and scalars and vectors. And I'm going to go through all possibilities. Now, dimension 1, I have no operators, not because I don't have scalars, but because of the assumption. I have the dimension 1 operator is one scalar. But that scalar, because of this assumption, transforms non-trivially under this GDM. And I've required that the operators ODM, as you can see here, I have yet another typo, ODM, this would be ODM. The ODMs are required to be singlets under this symmetry of the dark sector, whatever it is. A single field isn't. And so dimension 1 operators would be one scalar field, one vector field, they're not. If you have dimension 3/2, that's one fermion field, and then it doesn't appear because they're necessarily, because of my assumption, non-singlets on the dark symmetry. Dimension 2 are these, dimension 5/2 are these, possible dimension 3 are this mess, dimension 7/2 are these, and so you can go on listing these guys. I will stop with this. And now what I'm going to do is match them and see, well, what is the lowest dimension composite product of this times this that I can get, and again, I'm sorry, this is the that I can get, which satisfies all the symmetries, including now, because this will be a member of the Lagrangian, including Lorentz invariants. So the lowest dimension you can get is 2 times 2 is a 4-dimensional operator. I can multiply this by this by this, and I get a singlet. That's good. I can multiply this by this, and it's not good because I get a Lorentz tensor whose indices are not cancelled by anything, not contracted with anything. So this times this doesn't work. The earliest I can contract this with anything is with this guy over here. Which brings me to one question. How is this a singlet? Okay. This is the field strength of some dark vector, and phi is a scalar. This is not a singlet, and this, if it's just a U1 like here, would be a singlet. So that would seem to disallow this thing in all cases, but it's not. There is one, if X is a singlet, is a U1, corresponds to a U1, then X mu nu is a singlet. But it still can have other symmetries. can still have other symmetries. So under those symmetries, then x mu might transform into, I don't know, minus x mu, like a parity. And phi might transform into minus phi, the parity. So it is a lot. But there's another possibility which is also worth keeping in mind. If x is in a non-abelian gauge field, x mu nu transforms like the adjoint. Has a little index here, the adjoint. If phi a is also transforms non-trivially on the gauge group, on this gauge group, whatever it is, and in the adjoint, this object will be a singlet under the non-abelian gauge symmetry, be a singlet on the non-abelian gauge symmetry, and that would be the, and therefore it is acceptable. I bring this up because just to illustrate the fact that the symmetry in the dark sector doesn't have to be a global symmetry, it can even be a local symmetry, provided none of the particles are in are singlets under it. So, and what I'm going to do is list the very few lowest dimensional combinations that I have, again with the same spirit. Lower dimension combinations will lead to lower dimensional terms in the Lagrangian and to fewer suppressions of 1 over mediator mass as in their coefficients. Pardon me? No, this is not Lorentz invariant. This is not Lorentz. It is invariant under the gauge symmetry. But what I can do now is, if I'm looking at this interaction with the dark sector, I can contract it with the B mu nu in the standard model. I get a Lorentz singlet, and it's mediated by something. Okay?
Independently, as a dark sector term, will it exist?
The what?
In a completely dark sector term, it will contract with its own.
Yeah, in the complete dark sector, you can have that quantity squared, also mediated by whatever thing mediates this. Okay? In this fashion. Okay. So let's look at what we get. The lowest dimensional term is two scalar doublets in the standard model, 2 in the dark sector. The next orders have dimension 5 operators like this, and this, this, and this. And the thing that goes between them, and this is the picture I have in mind, that it talks on one side to the standard model, is a scalar that couples to phi squared and a scalar to psi bar psi. A scalar that couples to phi squared and to phi cubed. You might ask, well, what is it? And the answer is, I don't know. I don't know whether they're fermions or scalars. In some dark matter models, they're only scalars. In others, they're just fermions. In others, there's both of them. So this just describes generically, for any possibility, what kind of couplings can you have. If the mediator is a fermion, you get this type of thing, which will be something I will talk about extensively. If the mediator is a vector, you get a product of two currents. For consistency, the currents have to be conserved. I'm assuming that can be arranged in the standard model, in the dark sector. In the standard model, that's much, well, I cannot just assume it is conserved because I know all possible currents. One of them that is very useful is the current associated with B minus L. It's automatically conserved. And that's for consistency of having a vector field. Vector couples to conserved currents. And in this case, the vector I'm assuming is an abelian, corresponds to some abelian gauge group. They're other dimension 6 operators, and these are subleading in the sense that they're generated by the same guy coupling to the same type of fields, and so they will have higher dimension produced by the same type of effect, and so that's why I call them subleading. In the same way, here it is coupling the same fields but one with the derivative, and so I call it subleading. Operators like this are loop generated because I've assumed there are no mediators that behave like an antisymmetric tensor field. So these have names by now. This coupling of dark to standard model is called the Higgs coupling because cleverly it involves the Higgs. This is called the neutrino portal because, as you might guess, perhaps unsurprisingly, it involves a neutrino. This is called the vector coupling because it's a vector-mediated interaction. All of them have been studied extensively, some of them to death almost, like the first one. And in fact, right. But I will talk about this guy very briefly, very briefly. Once, from the point of view of effective field theory, I'm done. I exhibit for you the Lagrangian. The rest of the thing one can do is just apply it. It's another Lagrangian. I just do calculations. Okay, so I'm going to assume that the mediator is a fermion. I'm going to assume that there are two components in this, at least in the dark sector, one fermion and one scalar, so I can construct this. And therefore you have a tree-level coupling generated by this guy between the standard model neutrinos and the dark sector. This coupling will determine the relic abundance. Now, within this scenario, there is no direct coupling of the psi, the fermions in the dark sector, or the phi, the scalars in the dark sector, to the Z and to the Higgs. But these are generated at one loop. I'm briefly going to show that in a minute because I'm running out of time. The point of this is that the interaction that determines the direct detection of dark matter involves dark matter scattering off a nucleus. And this is achieved in this model only through the interaction of a mediation of a Z or a Higgs in the T channel. These interactions are automatically suppressed, which means that the direct detection cross-section is automatically small compared to the relic abundance cross-section. And this is what I liked about this model. We know there's a relic abundance of dark matter. We know it. But we haven't been able to see it. So this model automatically tells you that it's relatively easy to generate dark matter in the cosmos because it couples to neutrinos, but it's very hard to detect because its couplings to baryons are strongly suppressed. So the leading interactions are these: neutrino, phi dagger, psi, like this. The subleading interactions are these. They're suppressed by loops. These are not necessarily loop-generated operators. If you had a scalar mediator, it could mediate between two Higgses, a scalar, and two fermions. I mean, there's no problem with that. I am assuming that such a scalar does not exist. Okay, so I'm restricting further things. I can make a consistent model of it, so in that sense it's justified, but it's not the most general situation. I'm mixing a prejudice of what kind of mediators are there, what kind of new physics is there underlying, with the effective field theory approach. From this, I can do everything. I can calculate the relevant cross-section that determines the abundance of the dark matter in the current universe, and use the data from the Planck experiment to constrain the thing. And in this calculation, I'm going to assume that the fermions, the dark fermions, are lighter than the heavy fermions, than the dark scalars. If the guys are lighter than these guys, then along the way, these guys all decayed into fermions and neutrinos. So in this scenario, it is here. In this scenario, the dark matter is fermionic. You can assume the other way, but that goes back really to a Higgs portal dominated scenario that's been studied. So this is just an attempt to study an alternate scenario. That assumption. And so you get this type of constraint on the theory. This is the allowed value of this lambda f. Lambda f is related to lambda, which is the mediator mass. F is a coupling, and you have the masses of the two dark particles. You can do a more refined calculation involving the Z and the Higgs that are usually irrelevant because this coupling is very small, except when it hits the resonance, that is the mass of the Z and the mass of the Higgs. Here's the mass of the Z. Here is the mass of the Higgs. It's much narrower, so the effect is much more dramatic. And this is what you get for the limits allowed on this quantity lambda effective by this in this model. I'm going really fast because this is just applying something. The heavy lifting was done in selecting the operators. The rest is doing the plug and chug almost calculation in dark matter papers. Direct detection goes through these loop generated operators that couple to the nucleons via the exchange of the Z or a Higgs. The relevant interactions are of this form. This corresponds to the Higgs coupling. This corresponds to the Z coupling. And from it, you can extract with significant amount of difficulty because you're dealing with nuclei, not with protons, not with quarks, with nuclei, an expression for the direct detection cross-section. And the results are very simple. This is these are the limits. It's a little bit old, as you see, 10 years old. So this thing has come down to around here, kind of thing. But these are the various, for these various predictions, this is the cross-section. You can't read this. This is the direct detection cross-section predicted by the model. These are the limits on that cross-section from the experiments 10 years ago. The limits currently are around here, getting close. And these are the predictions of the model for it looks so jagged because of the difficulties in the complications associated with calculating nuclear cross-sections. There is also the possibility of indirect detection. That is, if these psis accumulate in the universe a lot, then and they coalesce in one place, like the center of the sun, they may, through an exchange of phi, annihilate into neutrinos. This is a relatively large coupling, and what the signature is, since these guys would be sitting in the sun, they would come together, annihilate, would be two back-to-back neutrinos with energy half the mass of the psi. Again, 10 years ago, the data was very sparse. Now it's a little bit less sparse, but the predictions and the data are still far away from one another. Okay, this is the end of my presentation. I'm sorry I rushed because I just have 4 minutes to conclude. So if you don't mind, let me conclude. And if you have questions about the dark matter model, we can ask later. Is that okay after the conclusion? So I can feel good about finishing on time, and I can blame taking longer on you. Okay, that's the plan. So let me conclude. So the EFT, I think, provides a very useful guide for studying new physics effect. It's very good. It doesn't have absolute precision of the model. It has many couplings that can be estimated or bounded, has one scale, and so on. You can extract very useful information, like the magnitude of this scale, or if you make a measurement and find a deviation from the standard model, or you put limits on the scale. And that tells you something physical about the new physics. But that estimate is not precise. If I say lambda is greater than 2 TeV, it doesn't mean exactly 2 TeV. There's a margin of error because I don't know the coefficients with precision. I can just put a consistency limit on their value. Okay, so the coefficients can be estimated, but they cannot be interrelated as they would in a model without making further assumptions. If you have a model, then everything is, some of the coefficients that you get would be interrelated. That's great. But if you have a model, why worry about the effective theory? Radiative corrections can be obtained. The effects of the renormalization group are limited unless lambda is much larger than b. That is, unless you run from a very large scale to the electroweak scale. Okay, they can be, but in this case, the 1 over lambda n per factor can suppress the overall effect. So the overall effect of the renormalization group running of coefficients are minor unless there is a huge mass gap. It has been extensively studied, this approach. There is even a working group, a standing working group in the community doing this. This is so there's a renewed interest in it, precisely because of the possibility of probing democratically all types of new physics using it. However, some studies are misleading or incomplete. That's decreasingly so, fortunately. Many experimental papers include only loop-generated operators. All the experimental papers, they put coefficients of order 1, and then they note they obtain very strong constraints on the scale of new physics. Those are misleading. Or sometimes the calculations don't include all relevant operators, which an exercise can be really scary because there could be very many included. But then the possibility of cancellations is disregarded. Cancellations are not a contrivance. Cancellations occur all the time in models, all the time in models. We had one expression, one of the exercises given to you in the tutorial about the strong interactions, ask you to calculate the scattering of pions. You would have found that the cross-section increases with the center of mass energy. And it does so precisely because there's a cancellation. It's not an unnatural fine-tuning. It's inherent to the structure of the theory. So cancellations can occur. Okay, they oftentimes are evidence or signals of something rather interesting or profound happening, but at the level of the effective theory, we might not be able to see this. On the other hand, ignoring the possibility might lead us into missing something. So if you don't include all the relevant operators, you can't see what possible cancellations could occur, and you might miss something. And there are things that have not been studied thoroughly. So finite temperature EFT is not very well studied. Effects of EFT on CP asymmetry in the early universe also have not been studied. And so there are also theoretical questions that people in the Institute can readily answer. Like, for example, why all dimension 7 operators violate B minus L, I should say B minus L. So this is one of many things. So I hope I've given you an overview over which I've rushed, and now I've overstepped 1 minute, which I apologize, of the field. The review by its own nature is incomplete and prejudiced. And so, nonetheless, I hope it has given you a flavor of the many exciting projects, the many interesting and challenging calculations and ideas that are involved in looking at this type of approach to quantum field theory. Thank you. Okay. Now, questions? Yes? Yeah?
No, not this one. This one. So there is a dip around 60 GeV, right?
Is it what?
There is a dip around 60 GeV because of
This is
threshold.
the Higgs. This is, I think, the Higgs. It happens at the mass when the mass of this guy is half the mass of the Higgs.
Yeah.
It's an interference effect that kills it. Yeah, sorry. Okay. Extracting an indirect detection signal for dark matter is very challenging because it's contaminated by astrophysical sources which we just don't know enough of. And so even the case, I'm telling you that there's a very smoking gun signal that is a monochromatic neutrino beam coming. There's more. It has to come out 2 neutrino beams going back to back. That's what you're supposed to see, right? That is, detecting one beam is very challenging. Detecting one beam on the other side of the sun when you're here is very challenging, okay? Other questions? Yes, sir.
So, yeah, I have a naive question, the two-part question actually. The first part is that you have calculated, you have shown that any discrepancy between the measured and calculated cross-section from LHC or any collider searches, that depends on how many effective operators we can write involving those processes. For a particular process, for a particular interaction, that interaction depends on all the effective operators involving the standard model particles. But the thing is that suppose we can attack that discrepancy, we can justify that discrepancy also by introducing any BSM particle.
Okay, that is precisely what this doesn't do.
Sorry?
Sorry, finish your question. Finish your question.
So first part is that how do we I mean what is the more precise justification introducing any BSM particle to justify that discrepancy between the experiment and the theory, or the actual reason behind that mismatch between the cross section could be an introduction or including all the effective operators.
Okay. So it's the same thing from 2 points of view. If when you say you include BSM particles, you mean, I think, I have a model, and I put in this model, and I calculate deviations from the standard model in that model. Okay. Okay. That is perfectly okay. That is perfectly okay. There's nothing wrong with it. The approach presented here is, what if you don't know what is the right model? If you don't know what is the right model, you can't write BSM particles because you don't know what they are.
Right.
And so, in that case, when you don't know, or you accept you don't know, or you decide you don't know, right? Then you do the effective theory because you don't know. If you include BSM in a specific model and you say, this is it, this is the extension of the standard model, we're done, the effective theory plays no role because there is no longer any BSM to produce any effective operators. Now, if you would like to see how your particular model looks like at low energies where we're probing, you can do that. You can derive from your model a set of operators that involve only standard model particles and have some coefficients. The difference between what I've been presenting here is that in your case, the coefficients are known functions of the model parameters.
Right.
Okay. In my case, they're completely unknown. But the calculation then would be the same. The only difference is your coefficients depend on, presumably, a small number of unknown parameters. In my case, all coefficients are arbitrary because I don't know what the BSM could be.
Okay.
Okay?
Okay. Yeah. The second part of the question is could an approach be to determine the energy behavior of the coefficients, the behavior of these coefficients or the cross section, how it depends on the energy, could be different for an effective operator approach or an BSM approach? Could this be?
So you mean the running of the couplings?
Yes.
So the running of the couplings can be obtained in two ways. Again, if you have a model, you just calculate. If you have these guys, you also just calculate. If they are represented, if they are representations of the same theory, yours is valid at all energies, the effective theory you derive from it is valid only at low energies, then the running you get at low energies would be this, for that scenario, would be the same as the one you get from the top-down approach. It might look very complicated, but it will be the same, provided all the calculations are done carefully. Okay.
Thanks.
Thank you. Other questions? No? All right. So thank you very much. It's been a pleasure talking to you.
So we will have tea after this.
Okay. Good afternoon, everyone. So by now, I hope you have all understood how to write down the effective operators. I mean, depending on the type of physics you are doing, and so what I will do, I will tell you how to connect the physics at different scales, and you see, I will talk about connecting the high energy scale to the low energy. Low energy mean you know that there are many low energy experiments are going on, and we have a large amount of data. So basically, this kind of exercise, either top down or bottom up approach, like if you can constrain the info, if you collect the information at the low energy and you can transfer it to as a information to the high energy, that will give you some sort of idea what to do at the high energy experiments, and the vice versa. If you find something at colliders at high energy, that will also help you to get some idea by this method. Like that will be the top-down approach. So collecting the information at high energy, transfer it to the low energy sector, and see what are the effects you are getting, and try to check by experiments. Okay. So these are basically complementary things. So what I will do in this talk, basically I will discuss about how this mechanism work. Okay. So as you know, that effective field theory is basically you can write down your set of operators at different scales. You can integrate out particles and of your choice, and you can just you pick up the particles whatever you are interested in, and you can write down the operators in a gauge invariant way. Okay. So this is what the effective theory, and why this is useful now by now, because you know that standard model is successful. It's a successful theory, and by now we know how to generate the masses for the standard model particles, and also we know actually we also know that it is clear to us the CP violation picture in the standard model. So a couple of things, I mean many things we know by now, and standard model, and in fact after the discovery of Higgs boson, it is more or less clear all the particle content of standard model by now we know. However, there are a couple of questions are left unanswered. It's basically you know that the existence of dark matter, neutrino mass, various other things are there, like why the CP violation that we see, like the baryon asymmetry that we see in the universe, that's also you cannot explain by the standard model CP violation. So these are some unanswered thing which needs to be answered. Now therefore what you can conclude out of this, that it might be the standard model is an effective theory, and it's valid up to some scale. Let's say you can pick that scale to be lambda, which is the new physics scale, and beyond that you can add additional degrees of freedom to the system, and you can write down your set of operators again, and you can do the things. Okay. So now but so far we have not seen, as you know, we have not seen any evidences beyond the standard model. So in that, I mean, so that you can that you can try to understand by assuming that maybe the couplings are very weak, or the new particles that you are expecting is very heavy, so that you cannot with the current setup in the experiment you won't be able to detect it. So if it's too heavy, then you can still you can live with the particle content of the standard model, and you can extend your reach to a high scale, and you can at the high scale also you can write down your effective theory. Okay, and that is what is the SMEFT, right? So basically that's what I mean the trick right now we are using. So and as we know that operator coefficients, that while you write down an operator set of operators, definitely you have to introduce the coefficient, and you know those coefficients will be scale dependence. It will be sensitive to the scale that you are working in. Okay, so that's precisely the interesting thing that will help you to connect the physics at different scale via those Wilson coefficients. Okay, or the coefficients of the operators. Okay. So like therefore it is useful to study the running and the mixing of operators coefficients, and like you can start with BSM scale, you can run it to the electric scale where the experiments are going on around, and also you can further connect it to the low energy where also you have lot of data and further experiments are going on. Okay. So so therefore that's the idea. So and as I said, we have lot of data available in the low energy sector which can be utilized to put constraints or to understand the physics by what would be the probable physics from low energy to high energy. Okay, so that's a possible way. So now, as you have seen that here I will try to connect the coefficients at SMFT, like standard model effective field theory, where you know that it's up to 1 TeV, let's say, since we have not found anything up to 1 TeV, it allows us to parameterize the effects of new physics in a high dimensional gauge invariant operator. That's what we call SMEFT, and you know the gauge group is the standard model gauge group. Particle contents are also standard model particle content. So you following this gauge invariance, you write all possible operator, okay, following various other things. So I'm not going to detail of those things. You know there are papers on it. And so what do you do here? You are assuming that you have integrated out the heavy scale physics, heavy like new particles that you have. You are integrating out those things, and all standard model degrees of freedom should be should contained within the framework, and either it may be the fundamental particle or it could be also the composite fields. So therefore, what you do? You write down the SMEFT as like your standard model effective theory, and then you have a tower of operators, high dimensional operators. That's what you do, right? So so these are basically all the operators are written in terms of the standard model particles. Okay. So this is what is SMEFT. Alternatively, what you can do, like it's alternative and also the complementary to whatever you do here. You can do similar thing to the low energy sector. Okay. So that will also help you, as I mentioned, to search for new physics. That's called low energy effective theory, or this is also sometime in the literature used as weak effective theory. Okay. So it's the operators here will be written below the electric scale. Okay. So that means you can understand then below electric scale mean few particle content you are removing from your list, right? So that means you will be removing W, Z, Higgs, and top. Okay. Rest will be there. So therefore, so symmetry group would be SU3U1 because you have all the SU2 content, it's not there, and so and that's what the LAFT Lagrangian will be. So it should be QCD, QED interactions, all the QCD, QED interaction in the standard model, and then you have some the term 3D operator which will be useful for Majorana mass generation, Majorana mass term, and these would be the high dimensional operator which are greater than greater than equal to 5. So so this is what the QCD, QED. So you see the particle content, you don't have here the top, and so all the other fermions are here, and then you have this part. Actually you can write as a combination of two, right? Like one part would be simply electroic part that will be coming, you can assume those operators will be coming from integrating out the W, Z, and top. Okay. And another part you can add another set of operators, those might be coming from the other new particles, those we don't know. Okay. So so that way you can divide this part in two sectors, like one is electroic and the other is BSM. Okay. So and for the electric sector, the calculations are readily available, like you know famous paper by Buras. I mean, you see for how to do the running and how to connect the coefficient from electric to low energy and all these things. For this electric sector is known, like the part associated with integrating out W, Z, and top. Okay. And so now what would be the dimension? This if you do power counting, this the coefficient should scale like 1 by V, okay, or 1 by V d, exactly if you write it d minus 4. Okay. However, if you are obtaining this, it is possible that you will be obtaining those effective operator via the insertion of SMEFT operators. So then power counting will change. So in that case, that would be the power counting, right? So you will have additional 1 by lambda factor, and that additional lambda factor you can write it like 1 by V by lambda, and then this whole power counting of this quantity of this coefficient would be like this. So you will have additional suppression factor that is coming from the that is coming as a V by lambda. Okay. So now so therefore now what will how does it help you? Basically, once you I mean this you can utilize RGE, and these coefficients you can bring down to very low energy from the electric scale, and that you can utilize for further study. Okay. So that's the basic idea behind all these calculations. Now this is the flow chart. I mean, like how exactly to do the actual calculation. Okay. So like low energy to high energy, or high energy to low energy. Okay. So various steps are there in between. So you can see, let's say you have some new physics scale which is not known to you. You put it at lambda, and you don't know what is the Lagrangian also. But once you know this, once you have a UV complete model, then you can do a matching of this UV complete model to your SMFT basis. Okay. And then further, what do you do from here? This is your SMFT basis. So set of SMFT operators, you know 59 operators are there, so you can write it down. And then what you do, first step would be you do a RGE, renormalization group evolution. That will basically, you can run down these coefficients to electric scale. Okay. That's the first step. And then what you can do at this scale, electric scale, you can match it to the effective operator associated, which should be relevant below the electric scale. Okay. So that matching you can do at that scale. Okay. And then, so this is your this is where you will be defining your low energy effective theory basis or weak effective theory basis. Okay. So that's matching you need to do. And then what you will do from here to a very low scale will be, again you will be using RGE. Okay. So that means from electric scale to this you need other, because here the operator might mix. Okay. If you don't do, if you directly come from here to here, you may be missing those operator mixing and all these things. Okay. Also, so this is one of the important point, that operator mixes here, this set of operators, among them they mix. So that contribution is relevant. At the same time, what is relevant is you might need to consider the running of QC decoupling and the QD couplings, because those, you know, if you, while you are going to a lower scale, they vary abruptly. Okay. So while you are going to a very low scale, you need to be careful about the running of the QC decoupling in particular. Okay. So you might need to consider that as well in your calculation. Okay. So this is the flow chart. Okay. That's how, if you understand this, you are done, at least from basic understanding point of view. Calculation is much more difficult, so that part is different, but at least understanding point of view, it will be done up to this. Okay. So now, how exactly this thing could be done in a realistic scenario, like consider like RGE like for the operator coefficients. So like I have written down this equation for SMFT basis, so you know 59 operators. So in principle, this is how you can write down the running equation of RGE equation for those set of operators or for those set of Wilson coefficients. So here gamma is basically the anomalous dimension matrix, right? That is needed for the understanding of the running of the coupling. Okay. So that's the one of the important part in the calculation. Okay. That you need to understand how to calculate. Okay. So this is what this basically tells you whether there are operator mixings or not. Okay. Also, I mean, it will basically give you an idea how the things are running from one point to another, how exactly they are connected. Now, what is that? What is this gamma? How do you calculate it? So gamma is nothing but you can define it like this, where Z is basically the operator renormalization constant. Okay. Now, this is how you define the renormalization of the Bayer operator. So Q, let's say Q0 is your Bayer operator and Q is your renormalized operator. So Z will be the renormalization constant. Okay. So then, so let's say, what is this basically? How do you define this renormalization constant? If you define an operator, let's say you define a 4-quark operator. Okay. So what you need to do? This is the matrix element. So matrix element of the 4-quark operator, and then what do? You will do corrections to this 4-quark operator. Okay. You will calculate the corrections, and those corrections, higher order corrections, might have divergences. Okay. Now the question is that how do you deal with those divergences? Now those divergences you can absorb as a renormalization of the operator. So within the, you define the renormalization constant, and within that constant you absorb those divergences. That's the procedure you can follow. Okay. So therefore the divergences here, whatever you will be getting from the loop calculation, you will absorb in the coefficients within the renormalization constant, and this is how you do. So what do you have? While you are writing a 4-quark operator, you will have quark renormalization as well, right? Because those quarks are bare quarks. Okay. So they are in the interaction base. So basically, you use the renormalization for the bare quark. So ZQ is the wave function renormalization. So you have 4 in total. So therefore, square root of Z for 4, it will give you Z square, okay, ZQ square. And Zij is the operator renormalization that you are absorbing, that you are introducing. So therefore, whatever the divergences you have within the matrix element of Qj, a part of it will be cancelled by ZQ minus 2, and the rest you will absorb in the definition of Zij. So that's the technique of introducing this thing, of utilization of how to utilize this operator renormalization. Alternatively, you can view it differently as well. This operator renormalization you can transfer as a counter term of the coefficient, Wilson coefficient here, right? Because you know what you need to do, you need to just define a renormalized quantity which is the product of this C I and the matrix element Qi, okay. So that's what you need to do. So therefore, whatever you defined here, it could be also alternatively could be defined by renormalization of Ci or counter term associated with the Ci, okay. How do you do it? You can understand it clearly. So let's say you introduce, instead of the operator renormalization, what you are doing, you are just defining a counter term associated with the coefficient Cj, and as usual you have the wave function renormalization associated with the quark, okay. These are the two things you are introducing. So now what you do, this thing, whole thing, like Ci, Qi, you will be writing like it's a 4-quark operator again, let's say we are considering, then you have ZQ square coming from the quark renormalization, and then you have Zijc, that will be the counter term you have introduced here, or the renormalization parameter that you have introduced here, right. So then this thing you can write in this form, okay. It's just simply addition and subtraction. So then this would be the renormalized one, this quantity, and then this you can treat as a counter term, okay. So this is how you can, the whole thing you can play. So now once you do so, then the whole thing Cj Qj, basically what you are calculating, this you can write in this form. So here you are not doing any kind of operator renormalization, instead you have introduced a counter term associated with the coefficient, okay. So then finally in one way, let's say in the beginning, this part you have obtained from operator renormalization, that part you have obtained from the coefficient renormalization. So these two things should be equal, right, because anyway you are talking about the renormalized quantity, this quantity you are talking about. So if you compare these two things, then you can say Zic like this renormalization constant associated with the associated with the coefficient should be equal to Zji inverse, okay. So that means that should be equal to the constant associated inversely proportional or equal to the inverse of the operator renormalization constant, okay. So that means these are connected. So in a way, if you have calculated one, you will be able to easily transfer the impact of it to the coefficients, okay. So what do you need to do therefore, in order to calculate the anomalous dimension matrix, because this thing would be associated with the anomalous dimension matrix. How? You know that I mean this equation you are familiar with, right? Mu dc mu this Ci is the bare coefficient, let's say, okay. So mu dc mu will be 0. So that dc mu Ci you can write from this, okay, and Zij you can simply split like this, delta Ij and delta Zij, delta Ij, because this is necessary, this will be, first term will give you the actual coefficient, and that will give you the corrected term or the counter term associated with the coefficient, okay. So therefore if you write it like this here, if you substitute it here, then this equation can be written like this, okay. So mu del Ci by del mu minus mu this quantity, and this is what is gamma ij Cj. So, gamma ij is what we have written down earlier as anomalous dimension matrix. Okay. So, gamma ij, how do you calculate therefore? You need to simply calculate these derivatives, okay, of the derivatives of the renormalization constant which you are, or renormalization of the renormalization constant of the operator, I mean constant of the operator renormalization. Okay. So, this Zij is basically you can connect it to Zij inverse. So, basically once you calculate the operator renormalization constant, then you are done, you will be able to calculate the anomalous dimension matrix, that is all. Okay. So, now just take an example like you take an SMFT operator here as an example, how to exactly calculate those matrix you can realize. So, let us say this is the operator, and then you are taking the corrections at one loop level. Okay. So, these are the corrections, these are the diagram, one of the diagram, important diagram, leading order that will contribute, and definitely this will have a divergence. Okay. So, now how do you absorb this divergence? This divergence you can absorb by defining a constant counter term like this. So, this factor here, so you are adding a counter term, and this counter term is defined such a way that, I mean that, so that the divergence here, UV divergence that you have will cancel. Okay. So, now you can also introduce, apart from ZB, apart from the constant associated with Cj, you should also introduce the renormalized coupling as well as the renormalized fields, right. So, all these things you introduce, and finally renormalized, I mean the effective coefficient that you will be getting is basically this quantity. So, taking into account all the wave function renormalizations. Okay. So, and this you can utilize to calculate the final anomalous dimension matrix, that is all. Okay. So, now we will as an example you can think of like 4 fermion operator. Okay. So, this is the interaction vertex, how do you write, and then counter term you will be able to calculate if you calculate the wave function, all the correction in external legs. If you calculate all of them, that will give you the counter terms, right. So, and then you calculate the corrections at first order, one loop corrections to all the diagram, this effective vertex. So, issue all possible corrections. This is with photon, and these are all with the gluons. Okay. So, so then you just all these corrections, if you this will contribute. So, adding this with this will contribute to your anomalous dimension matrix. Okay. I mean it will contribute to your operator renormalization, but finally you can convert it to you can calculate from there the anomalous dimension matrix, right. Similarly, if you consider psi square x, this kind of operator, it's like you can also calculate here the counter term by calculating the corrections to the external legs. Okay. And then finally, you can calculate the vertex corrections to this operator like with gluon and with photons. Okay. And this will contribute to psi square x, you can see it already. Also it can contribute to psi square, but for that you need to use equation of motion. Okay. And an additional thing like this set of diagram will contribute to this operator, and this set of diagram will contribute to this operator here. So, but similar this whole thing will contribute to psi square x as well as psi square. So, this will in a way will contribute to operator normalization as well as finally it will be converted to the anomalous dimension matrix. Okay. So, this is how this set of things I have written down for LEFT basis. Okay. So, suppose you have LEFT operators, set of operators with fermions, and for them you can do the corrections with photon and gluons. Okay. So, now matching. So, next thing, as you remember the flow chart I mentioned at one step, you need to do the matching. Okay. So, goal of the matching is to find out the coefficients at different order. Okay. In a fixed order perturbation theory or in any kind of matching calculation, what you do, the idea is to find out the coefficient at a different scale, right. So, so here what do you do? Basically what do you need to do? You need to just equate the amplitude, okay, at LEFT, use whatever the amplitudes you are calculating using LEFT basis of operators, that you can equate with the SMFT basis things, but all has to be renormalized. Okay. So, you need to add counter term and the full other whatever the one loop or leading order or whatever results you have, you need to add them and you need to equate them. Okay. So, this is what finally you can write down. So, you have 3 contributions, then you are adding the counter term that will partly cancel the divergences in your loop. Okay. And here also you have SMFT tree, counter term, and partly it will cancel the divergence of things, and the overall divergences, leftover divergences is expected to be cancelled within the whole thing. Okay. In a proper things it should happen. Okay. Otherwise you need to there will be problem. I mean, you need to rethink, or you are missing something or something else. So, in general you should expect this. However, in this case basically while you are matching doing a matching calculation from SMFT basis to LEFT basis, so that means what you are doing, you are equating a different operator contribution in SMFT to a single operator contribution in LEFT, right. So, therefore this is the matching equation you should write. So, Cij or Qj matrix element that you are calculating SMFT, it should be equal to a contribution or amplitude at LEFT. Let us say this I am indicating with I mean the operator, the single operator that I am targeting in LEFT basis, and that if you expand the left hand side, this would look like this. So, Cij, this would be the tree level contributions. If you have a tree level operator, I mean if your operator here, if you have some operator in a SMFT basis which will contribute to the LEFT things at tree level, then you will have some Cij 0, and then you need to add Cij at one loop level. That means the contributions that are from the SMFT operator, those are coming that will contribute to LEFT at one loop order, those part, and then you need to add the counter term. Okay. That should be associated with the tree level operator. Okay. So, this is how, if you expand this is left hand side will be associated with this, would be with the part of the coefficient that should be convoluted with the tree level coefficients, matrix element is given by this, and another part would be like if you do corrections to the effective operator, one loop corrections to the effective operator. So, when that would be relevant? When you have a Ci0 0, that means you have a tree level coefficient, I mean you have an SMFT operator which will contribute to your LEFT operator at tree level. So, in that case, if you want to do a one loop matching, you need to calculate the corrections at to these operators, SMFT operator at one loop level, which will contribute to your LEFT things. So, this is what the perfect matching calculation, you have to do it in this way. So, fixed order things, fixed order theory, you have to just order by order you have to calculate all the things, and then you need to match from both sides. Okay? That is the whole idea. If anyone have any difficulty, just this part is crucial. Okay? Anyone have any difficulty? Last part. So, you are doing a calculation, let us say matching at one loop level, right. So, one loop level mean, okay, let me write down. So, in general what do you do? So, let us say I am just talking in terms of, let us say full site, forget about for the time being SMFT or LEFT. Let us say you are doing a calculation where you have a full theory, okay, and you have a effective theory, okay, and you are doing a matching calculation. So, in general what do you do? So, full theory, renormalized things, let us say this is your tree level of contribution, and then you have one loop order contribution, okay, at one loop. You have some coefficients here, let us say, I am not writing those things. That you will be equating with the operator, let us say C, let us say CO, okay. So, but remember this C has to be C at leading order plus C at one loop level, okay. And then your effective operator, you need to write down O at leading order tree level and then O at one loop level. This is what the actual matching equation should be, okay. Now you expand both sides. You expand both sides, what do you have? M0 you will be getting like C0 O0, okay. Now if you write M1 or M1 would be what then? M1 would be equals to, because you remember these coefficients, whatever the coefficients you have here, here also you will have similar coefficients. So that means this will decide the order of the calculation, right. So that means now if you talking about, and also this will also have the similar coefficients. So fixed order mean this order you are matching and this order also you are matching. So that means same coefficient same similar coefficient I should equate, right. So that means M1, okay. So that should be equals to therefore C1 0, right, and then you have C0 okay. So that is what one of the term I have written down here, okay. So once you understand this, I mean then you will be able to do calculations. Only thing is that loop you need to learn how to do a loop calculations. So here I will take few examples like one of the interesting mode is B2S. It's a efficiency process and standard model is suppressed. So that's why we have a lot of expectation from this mode. So the SMFT, these are the set of operators in the SMFT basis which will contribute to B2S at tree level, okay. So you will have a tree level operator which can contribute to B2S process. In general I am talking about B2S, I will subdivide this thing like various mixing or semi-leptonic decay and so on, we can do that later. So here note that all the operators are written before the unbroken phase, right. So that means you did not have the operators are written in interaction basis, right. So you need to transfer it to the mass basis, because below electric scale while you will be transferring it, you will be doing it at the broken phase, okay. So that means you need to transfer it to the mass basis. So what do you need to do for that? You know the mechanism, right. You need to rotate the clever, okay. So and that is what you need to do, and finally I mean part of it will contribute also as a CKM element, but in general I am keeping it like just the rotation of the fields, okay, from interaction basis to the mass basis. So now for an example, like if you have an operator from here, like this is the operator written from here, okay. So for that if you introduce this rotation, so finally your coefficient should be like this, okay. So it's just the actual coefficient what you have in the interaction basis, that should be somehow I mean multiplied by this factor that you have here, the matrix that you have here basically. Okay. So so this is what you get. Now what I will I am going to, like, first thing is BS base bar mixing. Suppose you know what is the BS base bar mixing, right? So so this is the effective operator in LAFT that will contribute to BS base bar mixing. So these are the set of operators you see. So BS base bar mixing, simple tree level you can have, also you can have loop level contributions, okay. So so to BS tree level also they can give you BS base bar mixing, or it can come via loop, additional loop diagram, that will also contribute. So here I will talk about both the things like tree level contribution and as well as the loop level contribution. So these are the set of operators which will contribute at the tree level, okay. Or in general this is not what I mean by tree level, this is what I am saying, these are the in general the basis, LEFT basis, the operator is written here. Okay. So, the prime things you will be getting if you transfer PL to PR, okay, in this set of operators. So, now what are the operators that will contribute to this basis or BS-BS mixing at tree level? You can see from this list. So, these are the operators. So, you can see if you expand this, you can easily get BS-BS bar, BS-BS bar vertex. Okay. All these operators can give you. So, that means it can contribute at tree level to the BS-BS bar mixing. Okay. So, and if you do a simple matching, like if you just write down the operators and rotate the fields and match it with this operator following this, because it is a tree level thing. So, tree level you do not need to write down loop part. So, it is a straightforward matching. So, like this equation. Okay. So, and if you do so, you will be able to get this Wilson coefficients. Okay. And this I am getting by using this the relation of the product of the generators. So, this is give you a color suppressed contributions. So, 1 by NC is coming from these are QCD I mean so generator of SU3. So, you have this property. So, these are color suppressed contributions 1 by NC, but this is coming from Q8 only. You see you have TA here. And apart from this, I mean this again the coefficients as I mentioned will be obtained from the actual asymmetry coefficients by these rotations. So, you just by this S. So, actually you can get it. If you do a simple calculation, you will be able to reproduce it. And then there are other contributions which are relatively suppressed. Those could come from this operator here. You see, if you expand this phi, so this will also contribute to a leading order to the masses of the fermions. Okay, and then this is the corrections, and corrections will give you BS vertex. Okay, so that means this effectively will contribute to BS bar mixing as well. But these are relatively suppressed things. But here you see only these are the set of operators which will contribute. You do not see any contribution from C3 or C3 prime, and yeah, rest of the things are contributing. However, why do you need RG or running? That you will see in a while. If you calculate the RG, you will see because of the operator mixing, C3 will also contribute. Okay, so that's the importance of RG. So, you will see in a while here in this slide in particular. So, so this anomalous dimension matrix will be only as you have seen the corrections that you are calculating because of gluon exchanges and photon exchanges. So, basically it will contribute to your operator normalization here. This part references I will provide, you can check from there. And so, these are the diagrams effectively that you need to calculate. Okay. So, you have 4 quark operators, all the operators that you have seen is a 4 quark operator. So, you can calculate the corrections to QCD and QED corrections, and so basically that will give you the anomalous dimension matrix once you calculate all these diagrams. And if you then you write in matrix form and try to derive the anomalous dimension matrix, you see here this would be the form, and you see here it mixes, right. So, you see 2 3 is mixing. Also here here it should be like this, and this operator is also mixing. Okay. So, in alpha S as well as in alpha electromagnetic in QED all they mixes. So, that is where the role of RG is there. So, basically whatever if you have a direct matching, if you do not do the running, you may be missing the contribution of the operator, that is basically will contribute by RG. Okay. So, this is one of the thing, and one loop level, if you try to calculate the one loop level. So, these are the set of operators here it is written which will contribute, part of it will contribute at one loop level to BS bar mixing. Okay. So, here I pointed out this set of operators which will actually do the job. So, here you see the diagrams basically. So, this is the operators here, you see QQ bar and UU. So, here these are basically up type quark. So, here the contribution will come from the top, and you have a W exchange here, and this all these 4 operators can contribute here, and actually one can calculate the coefficients here and do a matching calculations. Okay. So, if you do the matching calculation, this would be the operator to this would be the coefficient to which this will contribute. Okay. So, and here Ixt is the enabling function. So, you see is the scale is here basically involved is mw square and mu w square here basically. Okay. Since you have just calculating the matching calculation at the electric scale. Later you can, if you run it down to mu b, then that scale will be introduced later. Okay. So, now another example is B2S LL. I know this is also an interesting mode, and B2S gamma. In particular, these are also efficiency processes and rare processes, and standard model is suppressed. Okay. Now, in this case, in general LEFT basis or WET basis, you can write down a set of operators which are I have listed here. So, most relevant are the one which is written here. So, you see in general we write it like 07, 08, you have seen in the literature probably 09, 09 prime, 010, 010 prime, and OS, OP, the scalar and the tensor operators here. And you see the primes are basically related to non-prime things with the PL replaced by PR. Okay. So, that is how things are distinguished from one another. And these are the operators. You can see here directly you will not get B2S LL, but in general QQ can form a loop, and then finally you will get a Z or photon, and that will give you finally LL bar. Okay. So, that is why you can get a contribution to B2S LL from this set of operators. Okay. In general you can generate this set of operators. So, these are all these operators are written in LEFT basis. Okay. You do not see any other particle. So, so what I will do, I will not talk about this set of operators. Actually, then it will be a huge numbers of huge number of operators are there, and a lot of contributions you need to track down. So, I will just focus on this part, which are the most relevant one. So, here again I am bringing back this set of operators which will contribute to your B2SLL at tree level. First we will discuss tree level contribution. So, so one by one we can go, like if you focus on these operators. Okay, you have QQ bar, this will give you a this can, if you expand it, it can give you a BS bar vertex, and then you have lepton L plus L minus you can get from here. Similarly, this operator also can give you a tree level B2S LL. This operator also can give you tree level B2S LL. Okay. So, these are the set of operators where you have the quark current contain a left-handed quark. Okay. Left-handed quark current basically V minus A type. Okay. So, that is why it is contributing to C9 and C10. If you recall the operator, it was PL in both the cases. Okay. Now, if you write down another set of operators like this, so you see here the quark current is right-handed. Okay. Here also the quark current is right-handed. Okay. And this will contribute to your, at tree level, it will contribute to your C9 prime and C10 prime. Okay. And then you look at this operator, this also have a tree level contribution to B2SLL, and this will be, I mean you can have like CSCP and or CS prime or CP prime, all to all this it can contribute. Okay. Then you have another set of operators which will contribute to B2S gamma in particular, or it will contribute to C7 and C7 prime. This you see this will be via W corrected diagrams. So, it will be via loop in general, but this will contribute to, I mean, but in general these operators, one of them is B2S gamma you can easily get like this operator, and this also with a W correction, W vertex correction. And another set is this one, you see d mu you have. So, d mu mean the covariant derivative, if you write down you have Z there. So, basically this will contribute to C9, C10 or C9 prime, C10 prime via this effective coupling BSZ. Okay. This you can get from this set of operators. So, these are all tree level contributions to B2SLL. And then anomalous dimension matrix, if you want to calculate, you need to calculate all these diagrams. Okay. And you will have a set of anomalous dimension matrix. Look at this reference if you are interested to check it, just look at this reference, they have calculated explicitly all these contributions. Okay. So, these are all you see corrections to the 4 fermion vertices. Okay. And here these are corrections to the all the other type of vertices. Okay. Here is these are all 4 fermion vertices, right. But these are different kind, these 4 fermions, these are also 4 fermion, but different type of operators are there. and also you can have like gauge dependent things and all these things. So, detail you can see here, so I am not going to discuss it here. But now you can do you can talk about one loop matching. So, at one loop level you can distinguish different set of operators, like you may have 4 permanent operator contributing to a 4 permanent operator like B, S, L, L. Okay. So, like here you have B, you see here you have a 4 permanent operator like this, which will contribute at one loop level. This you won't get at tree level, it won't contribute to B2SLL, but you have a TT bar here, TT bar and LL, that will contribute to your B2SLL in general. So, this is one loop contributions. Okay. So, these are the if you calculate this diagram, this would be the contributions. Okay. So, here enameling functions is there, and then you can have other type of contributions where you have only let's say instead of lepton, if you have 4 quark operator. So, 4 quark operator in general it can give you directly you cannot get a diagram like this which will contribute to B2SLL, but you can have like BS and then TT bar, it close the loop, and then you have a Z, and then you can from Z you can generate LL. Okay. So, that way it can contribute to B2SLL process at one loop level. Similarly, you match it to effective operators and you calculate following this method, you calculate the coefficients. So, this is the another set of coefficients that will contribute to your B2SLL. Similarly, you can calculate like right handed Z coupling. So, here you see TT bar Z. So, similar thing TT bar Z, this will also contribute at loop level to this O9 O10 operator. Okay. So, this is the diagram, relevant diagram. So, you can calculate, you can check the reference that I mentioned for the calculation. Another set of operator that will contribute to 07, 08, you see the operators here. So, you have TT bar loop, I mean BSTT bar. So, you can see here with this is the kind of operator, you can use Pierce transformation to get a operator like this, and this will contribute to finally to your B2S gamma. In principle you can from gamma you can also extract L plus L minus, that will contribute to your O9 O10 as well. So, but do the calculation and you can match it and you can get the coefficients. Another set of operator like this kind of vertex, these are the effective vertex here, SMFT vertex, and this again we can draw the diagrams, you can calculate it, and this is the kind of operator that I am inserting here, and this also will contribute finally to B2S. So, you can see finally all these things will contribute to 07, 08, B2S gamma G and all these things. Okay. Another finally you have another set of operators like magnetic moment operator, magnetic operators. These are this operator. This will also this can contribute to all these 4 Wilson coefficients. So, the diagrams are these are the set of diagrams. In principle, you can have so various. You see all the operators like with a Z here, Z gamma G, and you have with a W. This operator will contribute in this vertex. So, with a W you see here this and this. Okay. So, and other things are from this operator. So, again you need to calculate all the diagrams and then follow the matching equation and extract the coefficient. That should be the idea. And finally, once you have extracted all the coefficients, you do the running. Anomalous dimension are given, you just use those anomalous dimension calculated, or if not calculated you can do the calculation in principle following the method that I discussed, and you can get the coefficients at the from scale mu W, mu electric to the mu a lower scale. It could be in this case it would be the bottom mu B you can introduce, MB scale you can introduce. So, in general finally in the applications what do you do? Let us say if you have a set of operators, it has been calculated already. So, these are the set of operators that you have that contribute to B2SLL or B2S gamma, and for all these coefficients the gamma matrix, that means the anomalous dimension matrix, are calculated, and this is what the equations. So, you can relate therefore one of the operators from at a scale mu B, the coefficient at a scale mu B to the coefficient at a scale mu Z, mu equals to mz, that means electric scale. And further you can do one step more running from electric to your lambda scale, and you can get you can relate this coefficient to that scale as well. So, that's how you need to connect from one scale to the another scale, following here a two-step matching calculation. Okay, two-step you have to do as I mentioned, otherwise you may miss the operator contribution from the operator mixing. Okay. So these are the references from where which I consulted to prepare this lecture. So you see, I mean, one with low energy effective field theory, the operator matching, anomalous dimension matrix calculation by Manohar and his collaborator, and also like specifically for B2S and B2C, the matching to this sector is by Christoph and his collaborator, and this is also by Christoph and his collaborator. So it's a this is for anomalous dimension matrix and all this thing. So that's where I will end. I will not conclude anything. So just only thing is that you have to do calculations to get things under control. Okay, thank you.
Questions?
So I was very much clear, or feel free to ask question, no problem.
Sir, in the basis slide you have defined the NEFT and SEFT and you have connected the scales in terms of V.
It should be M by V, yeah.
So is it necessary to do in terms of V, or we can just directly write in terms of V?
No, directly in terms of lambda, how do you write? You do not have the scale lambda at all. In you have your scales are defined up to electroweak, right? While you are writing LEFT, you do not have lambda in your calculation.
So yeah, so only way we have to.
Your upper scale is electroweak scale.
Okay. Thank you.
So higher scale is V. While you are taking the SMFT, you are getting the contribution from SMFT insertion, then you have no choice, it's automatically coming, and then you are just rescaling it in a different way so that you can see the additional suppression.
Okay.
More questions? If not, then let's thank the speaker once more. And we have the honor of felicitating Soumitroda, and I would like to do that. Okay, so now we have a tea session outside, and after this we actually should come back, because there is a valedictory session where we have the formal ending of this whole program. And so so we break for some time, take tea outside, get a little more freshened up, and we promise no more lectures. And so yeah. Okay, so yeah, so we formally conclude all the sessions for this 5-day long program, and we have just one last session, but that is mostly Thanksgiving and distributing the certificates. So we come back after the tea. Thank you all.
completing the time.
Yeah, yeah.
No.
Okay, so good evening and welcome you all to the valedictory session of this GYAN program on standard model effective field theories and applications to Higgs, neutrinos and dark matter. We are especially happy that we have with us Professor Sukumar Nandi. He is the senior most faculty from IIT Guwahati from the Department of Computer Science and Engineering, and he is currently the Dean of Administration, and we are really happy that he has been able to come to this valedictory session in spite of his busy schedule. So thank you so much. Let's have a big round of applause for him. So before I give the vote of thanks and we start the formal valedictory session, I would like to request Professor Sukumar Nandi to say a few words on behalf of IIT Guwahati community.
Good evening to all of you. Professor Jose Wudka and my colleague, my friends, experts, all participants, and whoever I have not mentioned anywhere, any place, all of you, at the end of the sessions, I wish to thank you all participating in this program till the last moment, because till the last moment usually we sleep or we go for side visits. But today I am able to see big numbers of faces. That's good in some way, that the experts kept you energized. That is one. Other maybe the attendance criteria. I don't know which one. I assume the positive side. The experts have made you things more attractive. As a result, you are here and you are able to learn a lot. By the way, I happen to be a BSc major or honors in physics. I switched from the physics, pure physics, to the applied physics because of some other reason. Then I realized that applied physics I am not liking. Then I landed up in computer science. And then I realized that that is also not good. I started doing PhD in VLSI. So then I adjusted into the computer science and engineering. I use the word adjusting. True sense, physics, I liked it, I loved it. Now also I do it in different way. I use in all research and everywhere that my physics helped it, because I did too much mathematical physics. In the PSc honors, the mathematics was very nice. So I was liking that, and then I realized that application side is very important. So all experimental. Then I realized there is a problem. So let us switch to computer science. That is the things happen. But physics really helped me a lot, and physics built me things. Today I am happy to be here to address you in a program that to GYAN on a specific topic, where when I studied physics, that time I faced problem how to define a wave and the matter. So these two, that is particle property and the wave property, correct? Duality principle. There I lost it, now remain lost there. Different time we use different way explanation. Till now I don't know. You may know better than me, because I am no longer in physics, application of physics. But I realized that we computer science, communication engineering people, I also work in communication area, from VLSI to communication area, where we use the wave property more than the particle property. So that wave property is very interesting. Whatever equation we have learned, scattering and others, we are using. Here also you people are doing scattering maybe, and those scattering is different from what we are doing, but it can be explained in multiple ways. And this I wanted to emphasize is that theory is a necessity, and without theory, not a particular application is possible. And today I remain a domain where application is more important, but most of the engineers who did B.Tech or BE engineering and continue to the higher study, they cannot understand physics that much, which is also a requirement. So, my information to you, those who like physics and you want to tilt towards the application side, please tilt toward application side, because we need scientists who has little bit more orientation in pure, but want to apply in application area. That part is missing today. That is my observation I am expressing. It may be vary with persons, but my observation is that those are application scientists, those are applying binding models and other things. They ultimately go to PDE or ODE, then they use finite element techniques, solve the problem, try to model it, try to different models, and here you are also doing model. So, then model it and they approximate it, they come up to in the product form. And their theory, they happen very less. As a result, the product, quality product are rare. And it is happening only at places where there is good amount of theory persons exist. We need in India, in application science area, good amount of theory knowledge holder people. So, we are searching such people, because I am also part of the ministry in different forum, and we never get people who can help us in this area. But India is a problem, because everyone is king or queen, and that is another problem we face it. In collectively we don't want to work, individually we are remain alone. Together we can do lot, but at the end of the day, we individualism we show more. That is not the problem of the faculty or the whoever may be, that the system built in such a way, group work is limited. So, but if we, the future generation of you, future generation, we together can build our country, and that needs together to work. Hope this from which day? The 9 to this 5 days you have enjoyed nice discussions, nice learning. Please apply in different places, including teaching. Teaching is a very important requirement. Hope you will be able to disseminate all the learning. Thank you for coming to IIT Guwahati, participating here, enjoying the IIT Guwahati beauty. Thank you.
Okay, so this brings us to the formal Thanksgiving sessions. And first of all, and I mean, there is it is almost redundant, but to mention that we are all here because of one person, and he is Professor Jose Wudka from all the way from USA, and he has kept us captivated from the set of 10 lectures he has given, and I think he deserves another big round of applause. We must mention the presence of very energetic and very enthusiastic guest faculties that we had, and I would like to mention their names. Their presence have energized the discussions that we had these days. Joydeep Chakraborty from IIT Kanpur, Sanjoy Bishwas from RKMVU, Satyonarayan Mukhopadhyay from ISCS Kolkata, Shankho from IMSC Chennai, and our own Soumitra Da from IITG Physics Department. Now next, we would this program wouldn't have been possible without the hard work and the planning and the execution from the Center for Education Technology, CET. Professor Bharat, the head CET, who has communicated all our proposals to the central team and helped us in getting all the logistics correct. Let us have a big round of applause for Kaushik, who has been behind the scenes providing all the details of forms and etc. Kollol has helped us with all the technicalities, projecting the talks and helping us in connecting to the online members. We deserve a big round of applause for the videography team, who has live streamed it in YouTube and in other forums. We would like to thank the Hostel Affairs Board and Students Affairs section for arranging the hostel rooms for all of you. Hope they were not too bad. We would like to thank Gurupodo for the food that we had actually during these days. And now I think we would like to thank two very key persons behind their hard work was immense, and not only about managing the participations of offline candidates, but actually to also manage some of the contents that you see in my slides. And these two persons are none other than two of my very talented research scholars, and they are Ovik and Niloy. And I would like them to come forward, bring their own mugs, and I would like to request Jose to do the honor to felicitate these very young and talented people without whom this program wouldn't have been possible. I couldn't imagine doing anything close to the consistency at which it has been done without their constant effort and support. Yeah. Yeah.
They are doing themselves. See, they are giving to you and you are giving to them.
So you can imagine their importance and their presence. So maybe on the stage, Ovik. Yeah. And someone is there to take the photograph? Yeah, okay. So Ovik first. And Niloy. Yeah, now we have at the end, we would like to distribute the certificates to the offline participants. And to do the honor, I would like to request Professor Nondi, if it is okay for you, to distribute the certificates to the...
Few of them they will do.
Okay, all right, we can divide half and half.
They will do also their side.
They would also like to do? Okay, so as you wish. I mean, you are the boss.
Right.
So...
He is the boss and he is telling me boss.
Okay.
Because he is the man organizing this.
Okay. So, Manoj De from Guwahati University. So, he is a research scholar. Thank you for taking part. Shivam Bharma. So, we would like to request all the participants. Sirin Niraj, CS from IIIT Hyderabad. Ankit Das from IIT Kanpur. Ankit is not around? Okay. So, Shreya Kormokar. Yeah.
Independent. Sports. If you
Yeah.
are not in any country, you declare some other.
Okay, thank you. So Radhika Bhinze from ISER Mohali. Devolina. Avnish from IIT Guwahati. Shomodip Kundu from IISER Thiruvananthapuram. So you see, I mean, we have a whole spectrum from north to south. Shubhajit from IIT Guwahati. Yeah, yeah. Indrajit, IIT Guwahati. Krishna Tiwari, RKM VU, Ramakrishna Mission Vidya Mandir. Soumyajit Dotto from IISER Kolkata. Shongshaptok from IOP Bhubaneswar. Kaustav Mukherjee from ICS Kolkata. Nripanko Sharma from BITS Pilani. Nripanko is left. Okay. Riki Devi, Maibam Riki Devi from Guwahati University. Jose. Saurabh from Triple IT Hyderabad. Tisha Bishwas, IIT Kanpur. Debanjan Balui from IIT Kanpur. Debanjan? No. Sorry. Can I get it back then? Sitesh, IIT Guwahati. No? Okay. Shubham Shaha, IOP Bhubaneswar. Protoy from Kharagpur IIT.
Why not IIT?
Sorry?
Why not IIT?
Oh yeah, because Kharagpur is my hometown. So it comes first and then IIT second. Nayan, IIT Guwahati. Okay, all the IIT Guwahati people have left, Jose. Vipin, Vipin, aa jao. IIT Guwahati. Nitish Kumar Meher, IIT Guwahati. Rupak Chakraborty, Dibrugarh University. Tanmoy Dev, Guwahati University. He has standard model in his t-shirt already. Yeah. Rakesh from SRM University. He is not short either. Bikash Kumar Acharya from ISAR Berhampur. No. Okay, Jose, I think, yeah. Yeah.
No, they are also experts. No, they're not. He is forcing me. He is forcing me.
Saurabh Gope, ISAR Berhampur.
Another Saurabh. Saurabh with extra.
Prachiti P. Athaile, ISAR Thiruvananthapuram. N. Rajiv from PRL Ahmedabad. Manas Agarwal from NIT Agartala. Showman, IIT Guwahati. No, not there. IIT Guwahati people have left. Cheshta from IIT Gandhinagar. Sai Gade from University of Hyderabad. Debojyoti. Debojyoti is a faculty member in Bhattodev University, and it's a pleasure he has joined us. Behera Ram from IIT Guwahati. No. Okinchan Kundu. His affiliation is not written, so I don't know.
No, he is also like.
दीपेंदु उसमें लिख देना है, ठीक है. दीपेंदु IIT Guwahati. Pramod Sharma from ISAR Mohali. Shashwat Sharma from IIT Hyderabad. Maz Khan from IIIT Hyderabad. Orko Bhattacharya from RKM VU, yeah, from Saurabh Purohit. So his affiliation is also Rohan from IIT Guwahati. No, we are not that hierarchical. Yeah, I think this was missed because, yeah. R. Thiru Senthil from IOP Bhubaneswar. Yeah. Okay, so I think Professor Nondi can. No. We are halfway through. Good. So Jose again. Yeah.
So it's a musical chair.
Without any music.
Without any music?
Right. Yes. Clapping is there, but no music. Okay, Surendra Kumar Gaur, IIT Guwahati. Pradeep Singh Sekhawat from IMSC Chennai. Abhishek Kumar Singh from IIT Delhi. Sampriti Roy from ISCS Kolkata. Sonakshi Shaha from IIT Guwahati. Disha Bandopadhyay, IIT Guwahati. Disha is not around. Yeah. Devmallo from IIT Kanpur. Not around. All these people have already left for partying. Yeah. Himanshu from Bhattodev University. Chandan Duara from Dibrugarh University. Oh, he has also left. Yeah, I know. Dargi Shamir from IIIT Hyderabad. Chandra Prakash from IIT Guwahati. Utsav Dev from IIT Guwahati. Jainam Lakshmi Savla from Dibrugarh, right? Or IIT Gandhinagar, sorry. So your affiliation is missing. So we have to. Independent. Otonu Samanto from IIT Kanpur. Muhammad Isha Ali from ISCS Kolkata. Raiza Imtiaz from Dibrugarh University. Oh, okay. Isha, right? Raisa, okay. Come. Otonu is here. Okay. Otonu ke বাদ দিয়ে দিয়েছিলাম আমরা. Otonu Samanto, come. IIT Kanpur. Shantu Kumar Manna from ISAR Berhampur. Jose. Shontu Kumar Mannar. Is that the correct pronunciation? So my apologies. Yeah. Shontu. Suresh, IIT Guwahati. Dipankar, IIT Guwahati. Lipika, IIT Guwahati. Rishikesh Deka from IIT Guwahati. No, he is not. Okay, so we are done and we are dusted. I mean, essentially, this is the end of the program, and yeah, the. Okay. No, but before you say anything, so I would like to thank all the participants, for joining us and making the sessions extremely exciting. So this was very encouraging for us. I mean, we have our tails up, whatever that you say. Okay.
So I would request Professor Joydeep Chakraborty to felicitate Professor Subhaditya Bhattacharya for conducting this wonderful course. So.
And please give a round of applause for Professor Subhaditya Bhattacharya, because he has made the proper balance of not only organizing but also having these 5 lectures also. So big round of applause for him as well.
So, okay, with this note we close it, and we wish you a happy and safe journey from wherever you have come, and we hope to see you again on some other occasions. And if you have questions on the content that has been discussed, you can always reach us via emails. Yeah. Okay. All right. Thank you so much.